Right, maybe we should start just to be on time and to avoid to be cut at the end of our session. We can start speaking a little bit while the remaining participants are joining us. Welcome everyone to our Cosmography with Gravitational Lensing parallel session. I'm Claudio Grillo and I'm co-chairing this session together with Mimosa Fitzi. Mimosa, if you want to introduce yourself as well, you say a few words.
Thank you, Claudio. I am very glad to be among you in this afternoon session. And with Claudio, we'll do the best to have a successful meeting. I wish you successful discussion and all of us. Thank you. Maybe Claudio will give some
information about, yes. So we will have 8 invited and contributed talks. The length of the talks are between 20 and 25 minutes. We will give all the speakers 5-minute notice when they're close to the end of their talk so that they can conclude. And the last 5 minutes will be available for questions and discussion. I think everyone can switch on and off their videos and microphones. Probably a good idea to ask questions is to raise your hand, and then we will give you the possibility to ask your question or to make your comments one after the other. What else? The meeting is recorded, so the recording will be available later on the webpage. We open some breakout rooms in case you have urgent questions you want to discuss outside the main session. You can freely move from the main room to the breakout rooms if you need to discuss something with the other participants. And I think there are no other general announcements to make. So probably we can start. Our first speaker is Qifan Chen with an invited talk on the H0 measurement from time-delay cosmography. So Qifan, you can share your screen. And
okay, thanks, Claudio. So are you able to see my screen now?
We do, yes.
Okay, great. Okay, so I started now. Okay, so hi, my name is Qifan Chen. I'm the postdoc at UCLA working with Tommaso Trail and in collaboration with the TD Cosmo collaboration. So my work focuses on using the independent data set from adaptive optics imaging to constrain the H0 and contribute to the joint H0 effort inside the TD Cosmo team. So today I'm going to talk about our H0 measurement, the systematic check, and my interpretation of our results. Okay, so Hubble constant is one of the most important parameters in the modern cosmology because it not only sets the age, the size, but also the critical density of the universe. So there has been substantial improvement of the H0 measurement in the past 10 years, especially on the one hand, the H0 inferred from the cosmic microwave background obtained from the Planck satellite, assuming a flat lambda CDM model is robustly and precisely around 67, which is later confirmed by the Cpl Cosmology telescope plus the WMAP, assuming a flat lambda CDM model. So on the other hand, the local measurement from the supernova calibrated by the Cepheid is more than 4 sigma away from the Planck readout, while different calibration by the tip of very giant branch yield the H0 readout just right between the CMB and the Cepheid. So therefore, using the independent methodology is crucial to overcome the unknowns. The HOLICA collaboration has presented the H0 measurement by using 6 strongly lensed quasar to measure the H0, and it is very consistent with the result from supernova calibrated by the Cepheid. So in the past 2 years, we have went through a lot of systematic checks. So in the following slides, I will start from introducing the basic idea of the time-delay cosmography. Then I will present the systematic check we have done and give my view of the current status of H0 measurement from the TD Cosmo collaborations. Okay, so the advantage of using strongly lensed quasar is that it does not require the calibration and only depends on the single geometry and general relativity. So given the variable source in the background, when the light passing through the foreground galaxy with a different trajectory and the gravitational potential, you will arrive at different time, and hence we can measure the time delay. And the longer the time delays are, the larger the size of the lens systems are. The information required to determine of the size of the lens system are the time delay, the mass distribution, and also the study of the environment, which is also affect the overall size of the lens system and the determination of the H0. Okay, so let me start from the time delay. So the time delay measurement require long-term monitoring. So the bottom figures show that the 1 or 2 data point per week over several years. So one can see that we can construct the light curves. From the light curve, you can see even by eye that there is a time delay between the last light curve. You can see the yellow arrow and the first 3 light curves. So this is an example of the RXA 1131, and the time delay is around 90 days. But as you can see, it is very time consuming to obtain time delays if we do 1 or 2 data points per week. Okay, so the modern time delay monitoring is using the high cadence with the daily monitoring. It can capture the fast variation of the quasar light and hence measure the time delay within 1 season or 1 year. The left figure shows the MPIA 2.2 meter light curves from the Cosmography program for one of our objects with the cadence of daily monitoring. So you can also see that the time delay by eyes from the arrows. The program is aiming to obtain the time delay of 20 to 30 lenses in the south. And the right figure is the LCOGT key project led by me and just beginning this year and aiming to get the time delay of 50 lenses in the north in the next 3 years. So the next key ingredient is a high angular resolution imaging. So in the past, when we only have a 4 lens quasar precision, many lens models can reproduce the quasar position, so there are a lot of degeneracy. However, with the entire Einstein ring where we have thousands of pixels, it can reject to simplify mass model and place the strong constraint on the mass distribution. And another important information is the environment. So we can use the galaxy around our lenses to determine whether the lens system is embedded in the underdensity or overdensity region by comparing the number counts with the control field. So the environment information will also affect the size of the distance and hence the H0. So when combine all the information, the time delay, the lens mass model, and the environment study which constrain the kappa external and the redshift of the lensing galaxy, we can put tight constraint on the time delay distance, which is composed of the distance to the lens, distance to the source, and the distance between the lens and source. So the time delay distance is inversely proportional to the H0. So in addition to the time delay distance, when combine the velocity dispersion of the lensing galaxy, one can further determine the angular diameter distance to the lens. You can see the dependence of the kappa external is canceled out when you divide it by the time delay with the velocity dispersion. So the angular diameter distance to the lens, the DD, is insensitive to the mass along the line of sight, but depends on the anisotropy in the stellar velocity dispersion. So typically for single aperture velocity dispersion, we can measure the DD to 50% per lens, including the anisotropy parameters. So let me summarize. For each lens, in general, we can compress all the information to the 2-dimensional d delta t dt plane and use them to determine the Hubble constant. Since the d delta t can be very precisely determined to 4 to 7% for each lens, and dd is around 50% when we marginalize over the anisotropy parameter, then the main information which comes from constraint H0 is from the d delta t. Okay, So this is the basic idea of how we constrain the Hubble constant. So the next is that we have went through a lot of systematic check. The first one is that the main systematic check we have done is by using an independent imaging data set to determine the mass distribution of the lensing galaxy. So we use adaptive optics imaging collected by a strong lensing high angular resolution program led by my previous PhD supervisor, Chris Fasnet, to determine the mass distribution. So the advantage of using AL imaging in the right-hand side, right figure, is it provides higher angular resolution than the HST imaging. Okay. So from the result, we see that so in the left figure, we show that when comparing the result with HST imaging, the AL imaging can provide 15 pitter constraints on the tiny distance than HST. In the right figure, we also show that the precision of the lens quasar position, which is used to calculate the time delay, is better determined with the AL imaging than the HST imaging by a factor of 5 to 10%, 5 to 10. So AL imaging is really a nice data set to check the possible systematics. So we use the 3 lens systems with Keck AL imaging in the top row to constrain the Hubble constant. And then the results show that by combining the 3 lenses, we found that H dot is 75.6 plus minus 3.2, which is consistent with HST H dot result from the HST imaging. So another systematic check we have done is also called the microlensing time delay effect. In 2018, the Ty and Kochanek proposed that if the quasar accretion disk can be described by a lamppost model, which means that the variation of light emitted from the center can heat up the accretion disk coherently depending on the distance to the center. So since the caustic generated by the star inside the foreground lensing galaxy has a similar size of the accretion disk, it can magnify the light from the accretion disk and increase the light contribution from the accretion disk, and which has delay like with 1 or 2 days depending on the distance from the quasar center. So it can contributing to the total light curve. It can shift the light curve and increase the uncertainty on the time delay measurement. So we examined the effect on the inferred distance and found that for long time delay lenses, they are almost unaffected. You can see that the left figure with 90 days time delay, we show that the error on the time delay distance with or without considering the microlensing time delay effect, it is almost identical except slightly degrading on the precision. So on the right hand side, the figure on the right, on the other hand, for the right figure with the 13 days time delay, they are almost just broadening the air. So it is very easy to understand. For example, if a lens has a 100-day time delays, 1 or 2 day shift because the microlensing time delay effect doesn't really impact the determination of the time delay distance. So we further examine if we have any bias regarding this different mass distribution. As I said before, the Palomar model and the composite model, which consists of the star and NFW profile, are well supported by the observation and theory. So in the TD Cosmo 1, we see that they both very consistent H0. So you can see for the left-hand side, the Palomar model for with the 6 lenses, we obtained the 74.2, and then the right-hand side, the composite model, we got the 74. So they are really agree with each other. So I have to say the result can be different, but the excellent agreement indicating that our H0 measurement is very robust against the different mass profile. But extraordinary claims require extraordinary evidence. We further took one further step to relax the assumption of the mass profiles. So we transformed the Palomar mass profile via the mass sheet transformation, which is a well-known mathematical transformation operated in the projected mass distribution, such that it can the new projected mass distribution can produce the same imaging. So the left figure shows that transform projected mass profile, which you can all the different line here in the left figure, they can produce exactly the same imaging. The physical picture can be well approximated understanding by the right figures. In the projected 3D space, when with the velocity dispersion information, the distance between the lens and source is degenerate with the lambda in parameter, which the lambda in is used to describe the mesh transformation. So which is unconstrained by the imaging data, while the angular diameter distance of the lens is almost invariant. So basically, it's changing the source, the distance to the source, the source. So again, in the left figure, we can see it more clearly. So although the d delta t is fully degenerate with the internal mesh transformation, the dd is insensitive to the internal mesh transformation. But DD2 slightly depending on the anisotropy parameter, depending on how we observe it, the aperture size, how we obtain in the velocity dispersion. So in the right figure, as we showed in the previously, the lambda in is degenerate with the distance ratio. So if we have, if a cosmological model is selected or the external data set is used to constrain the distance ratio, then we can infer what's the lambda in parameters for every lenses. So to further constrain, because the data, at least for the single aperture velocity dispersion, we don't have the anisotropy information, and the internal mesh transformation cannot be break by the imaging data. So one way can constrain it from the population level. So assuming that the elliptical galaxies are self-similar, we can use the non-tangent lenses such as select lenses to constrain the parameter from the population level to point of view. So this is the summary of what we have. So first, if the galaxy can be described by a power law, a composite model, the results are robustly agree with the supernova calibrated by the Cepheus. In the case that if we relax the assumption of a well-motivated mass profile, which means that we allow the mass profile can deviate from such as the NFW profile, then the result depends on the anisotropy and the internal mesh transformation, the lambda in parameter. As I showed in the previously, under the internal mesh, the main information for constraining echelon comes from the angular diameter due to distance to the lens, and which is does not affected by the mesh transformation. But we still need the anisotropy information. So if we assuming that the select lenses and the TD Cosmo lenses share the same anisotropy property, we get the 73.3 plus minus 5.8. So which the uncertainty is much larger, but the result is still consistent with what we get in the previous. However, if we assuming that the select lenses and the TD Cosmo lenses share the same anisotropy and also the radial mass density profile, which used to determine further constraint what's the lambda in parameter, then the result shift to the 67, which is considered consistent with the CMB. So if the truth is that the select lenses and TD Cosmo lenses do share the same anisotropy profile property, then it hints that there is a radial mass density evolution between the select lenses and the TD Cosmo lenses. But we don't know yet because this is the select lens, the anisotropy still come from the select lenses. So the anisotropy determined directly from the spatially resolved kinematics will be very important to check this assumption. So the two common questions usually I got is that, is our echelon measurement robustly enough against the internal mesh transformation? So my answer is that for individual lenses, the main information for determining the echelon come from DD, which is insensitive to the internal mesh transformation. So the second question I usually get is that can population information bias echelon result? So usually elliptical galaxies are usually self-similar, but yes, if there is evolution. However, once the spatially resolved kinematics data can be obtained, one can determine a DD without the need of the population information. So the next talk, Akin will talk about this. So I will leave that to Akin. So for future perspectives, that we will have much more lenses from the kappa. So kappa is the kick all sky precision adaptive optics will deliver a lot of sharper imaging. Because now for some of the AL system, we cannot find a tiptoe star nearby because of the limitation of the instrument. But in the future, for the kappa will arrive in 2023, then we will get much more high resolution air imaging data. So this is the summary. So strong gravitational lensing is very cost effective. So we can achieve the 1% accuracy if we keep going, and we have more and more IFU data to further constrain the internal meshing and anisotropy. And this is the figure from the Simon's paper in the 2021. He showed that if we have 40 lenses, TD Cosmo lenses with the IFU data, we can reach to the around 1-2% level of H0 measurement. Okay. So yeah, so I will put the summary slides here. So if you have any questions, I can take it now. Thanks.
Thank you, Chifan. Perfectly in time. Any questions? You can either raise your hand, write in the chat, or just unmute your microphone if you can. I have a question, Chifan. Can you tell us about a little bit more about the new sample of lenses? You were telling us that you will look at 15 new lenses in the north. Is that correct? How do they compare to the previous lenses? Do they have the same average redshift? Do they have the same values of Einstein radii? Do they differ in some sense, or what is the new data set that you are collecting?
So so the next so the data set we are collecting right now is so there are several. The focusing is on the quad lens system for now. So they don't have the same lines and radius, but they do have the quad system, and this is the reason why because the quad system has more constraining power from the time delay. So we usually start for the north lenses because for the south of a Cosmography program, they cannot observe the lens in the north. So we are targeting a lot of lenses in the north. So they can be used to determine the. So usually we start from selecting the lens with a much brighter quasar, so it will be easier to get the time delay. Yeah.
And the lenses are more or less of the same redshifts as the previous one in terms of distribution? No?
No, I don't think there are any specific choice of the redshift because I think that this is choice by how bright the quasar. So it's not determined by the redshift. Yeah.
Okay, thank you. Any more questions for Chifan? Well, if not, thank you, Chifan. Thanks a lot.
Sure, thanks. So I will stop sharing now.
Yes, please. And then we can probably move to our next speaker. Well, perfect. Ken Ulderim and time delay cosmography in the age of JWST.
Yeah, well, just give me a minute. Why is this? All right, I think this should be working now.
We can hear you, so please.
Sorry. Sorry, I tried to move the slides with my. Why is this? It's somehow. That's weird. Let's try. Maybe try it from this. Okay. All right. Do you see my?
Yes.
Presentation? All right. Okay. Okay. Thanks, Claudia and Mimosa, for organizing this and for the opportunity to present to you some aspects of our most recent time delay strong lensing efforts within the strong lensing group in Munich. So with Sherry and I and various other people in our group, but also within the Holy Cow / TD Cosmo collaboration more general. So In this talk, I will try to give you a brief recap of our concerted efforts to constrain H0 to the percent level in the future, and how this will eventually become available or become feasible with time delay strong lensing, and particularly by means of vastly improved kinematic data from the next generation of telescopes. So Stefan also already covered much of the introduction. I will only really do this very shortly and to provide you a bit more context on what we're trying to achieve. So yeah, most of you should be familiar with this figure by now, I guess. It's from Adam Rees and his collaborators, and highlights basically the discrepancy in the H0 measurement from early and late type cosmological probes. And you can see the difference, the 4.4 sigma difference between both, and which seems kind of daunting at first, I have to admit, but let's remember what we actually see here, right? So the local H0 measurements, those are based on the physics of stars and galaxies mainly. So depending on whether you do it with time delay strong lensing or with the supernovae. And on the other hand, all these early type cosmological probes, they're basically, for instance, the CMB, that's an afterglow of an event that's 13 to 14 billion years old. So these methods, so they are entirely independent, but yet agree within, you know, a 10% difference, which is actually a remarkable achievement if you think about it. Nonetheless, right, and with that being said, let's also remember what is at stake here, which is the standard cosmological model, and which is why this discrepancy has really caused a lot of heated discussions lately at whatever cosmological conference you've been attending to. So of course, each camp, I mean, if you view these presentations, each camp really feels very strongly about their own science and about the science of the others. But there is certainly some consensus within the community that there are probably only two ways out of this problem. One, of course, is that there could be hidden unknown systematic uncertainties, either in one or in several of the methods, such that those may meet somewhere in the middle. And the other one, of course, the more interesting one, is that there would be cosmology involved beyond the standard, beyond our standard model. So whether that comes from additional relativistic particles or something else. And both avenues are actually explored, but given that the latter one, which involves, you know, a thinking beyond our standard cosmological model, and which at this stage, of course, also involves a lot of speculation, much of the recent developments basically evolve around assessing the systematic uncertainties in either one of the methods. And just to give you an illustration of what this can, what kind of impact this can actually have beyond the realm of time delay strong lensing only. So this is the latest figure by Wendy Friedman and her collaborators. And we know that the distance ladder is basically a three-step approach, right? So where we have pairs of geometric and Cepheid-based distances, and then Cepheid and supernova-based distances, and finally we link then the supernovas to the redshift and aim to constrain the Hubble constant. However, if you go ahead and just replace the first step, so instead of using Cepheids, you anchor the measurements by means of the tip of the red giant branch, then suddenly what happens is that all of your H0 values move to the lower end of the spectrum. And at the top panel, what you actually see that this new H0 measurement by means of the tip of the red giant branch is actually even less prone to where these red giants are actually located. So more or less independent from their host environments, as opposed to, for instance, the Cepheids, which show a much broader spread. So the basic message is that it is not clear at the moment why these measurements would or should differ from another, right? So, but what is clear at the moment is that both anchors are really in agreement out to distances of about 7 to 10 megaparsecs, but they start to deviate from each other further out, and this basically then trickles down to different H0 inferred values at the end. So this makes it, incredibly. I mean, this is incredibly difficult to understand. What the physical source behind this difference between the Cepheid-based H0 values and the TRGB-based H0 values is. But it just gives you, a very powerful example of how much of an impact basically these systematic uncertainties, which we're trying to assess, with improved data, with improved modeling machineries, depending on which methods you use, on what kind of impact may it have. And actually, if you now use the TRGBs, this 4.4 sigma discrepancy is no longer a 4.4 sigma discrepancy, but the TRGB inferred H0 values, they only deviate from the CMB by 1.3 sigma. And given this figure by Wendy, I mean, it is apparent that there's a need for other distance measures in order to resolve this H0 crisis. And thanks to Sifan's nice introduction, we now know that time delay cosmography basically provides such an effective one-step distance measure. I could skip this, but I will do it anyways in case people have just joined recently or are still rather unfamiliar with the methods. So really short, so when the line of sight to a distant source of light is well aligned with an intervening mass system, and this, in our case, this is always a foreground lensing galaxy, multiple images appear to the observer, and of course the arrival times of the images then depend on the interplay of the geometrical and gravitational delays specific to that particular configuration. And of course, if the emission from the background source is time variable, those different images that you see, given the time delays, will also flicker with a given time delay. And we know that in the simplest case, that this time delay distance, which is basically a combination of three different cosmological distances, is inversely proportional to H0. So to provide a stringent measurement of the time delay distance, and hence H0 basically requires not only a precise measurement of the differential time delays, as Sifan has shown you previously, but also a really accurate description of the gravitational potential of the foreground lensing galaxy, and of course also a proper description of all mass along the line of sight. So we know from Sifan's talk that all the ingredients are basically there. So for employing strong lensing for cosmological purposes, of course, the imaging, to identify the lens and the lensed arcs and the image positions and all that other stuff, which all holds valuable information regarding the gravitational potential well. Then, of course, the high cadence monitoring to measure the time delays. And then line of sight imaging and the spectroscopy to measure all the mass along the lens line of sight, and last but not least, of course, also stellar kinematics, which will come later. And given all our observational advances, and also all the different modeling machineries that have been developed in the meantime to properly model these things, this all basically culminated in the Holy Cow collaboration, which more recently presented its important result, basically a 2.4 precision measurement on H0 and flat lambda CDM on the left-hand side. You can see that based on a sample of 6 strong gravitational lenses. And given that measurement, if you now just place this, if you just neglect what I've shown you earlier regarding the TRGBs and stuff like that, if you just simply compare this to the common early type measurements to the CMB, then this is basically, so the H0 values from Holy Cow, they are totally consistent with that, for instance, from the local distance ladder. And they're also in conflict with the CMB measurements. And even more so if you combine all the late type probes against the early type probes. Okay, so time-related strong lensing is really effective, but it's also prone to modeling assumptions and uncertainties. And Stefan already introduced this, the mass sheet degeneracy, more commonly referred to as the mass sheet transformation, which is basically a transformation of the mass density profile, which can then be compensated by a respective shift and scaling of the source position and size. And with the latter being basically observationally inaccessible, one has to fix the mass density distribution to provide, to break this degeneracy and to provide a high precision measurement on H0. And this has basically done with, within the Holy Cow collaboration by fixing basically the mass density distribution to a power law composite profile. You then infer the H0 precision measurement of 2.4%. But we know from the mass sheet degeneracy that by introducing an infinite mass sheet, for instance, you can basically, so by adding additional freedom into your mass density distribution, you can basically shift the inferred time delay distances and hence your H0 values to whatever degree you would like, more or less, given that the lensing data is mostly insensitive to these shifts. And what you see here is basically a figure from Stefan's publications, where you see the degeneracy between the lens distance, the time delay distance, and lambda int, which is basically the strength of this mass sheet. So again, strong lensing is incapable of breaking these degeneracies, and given these findings, all the Holy Cow measurements have been revisited by Simon and the Cpl Cosmo collaboration, and you're already familiar with this figure. So if you go, so the top basically shows you the Holy Cow measurements by assuming a certain density profile. If you relax that profile, you basically should not only shift the mean value, but you also increase the uncertainties related to that, and you end up with a measurement that is no longer at odds with the CMB. So in order to solve this whole puzzle, we know that stellar kinematic data, which is an additional tracer of the underlying gravitational potential, that this is necessary. And there are two ways out of that. One was introduced by Simon. So basically you can take external data sets, try to infer either the mass profile or by means of the stellar kinematic data, the orbital anisotropy, and then use this as a prior within a hierarchical framework to further constrain the models for the time delayed lenses. However, there's a parallel path, which is you go straight to the time delay lenses and you try to observe, spatial resolved kinematic data of these time delay lenses. And this was basically not capable, this was not feasible until now because of the limitations of current observational facilities, but it will become feasible with the next generation of telescopes, whether that's JWST or any ground-based 30 to 40 class meter telescope. And what we did is we tried to do some forecasts with JWST, given the imminent launch. And JWST is particularly suited for this purpose because of its near-spec spectrograph, which has really a wide wavelength coverage in the infrared. So you can go ahead and aim for the absorption line features for all these lenses. It also has a wide field of view, which covers everything roughly within the Einstein radius. And it has a great spectral and spatial resolution. And in order to assess the constraining power from JWST data, we went ahead and tried to see what this basically brings to the table by doing an exercise with one of the strong lenses from the Holy Cow base sample. So this is basically RxJ1131, and this is the original HST imaging. And just to give you a sense of what the JWST field of view will look like, I just overplotted that in blue on here. But we don't have real data in hand, so we had to mock up the data. I won't bother you with the specific details of that, but it's rather straightforward. So you basically know what the surface brightness distribution looks like for this particular galaxy from the HST imaging. Then you can translate this into a into a signal to noise map, given JWST's specifications, and then you can play around with the exposure time to reach a certain signal to noise level. And by assuming some dynamical, arbitrary dynamical parameters for the orbital distribution, you can end up with a kinematic map which is shown here on the right with various, noise realizations. So what we did then is we went ahead and basically remodeled all this based only on the lensing data and based then on the joint lensing and stellar dynamical models by taking into account the JWST-like stellar kinematics. And what you see here is a fit. So the best fitting predicted kinematics based on the composite model, which was our actual input model, and the Palomar profile, and then the residual maps. And the reason we did this is because the kinematics are basically a very reliable 2D tracer of the underlying gravitational potential. So it allows you, as you can see even from the predicted maps, it really allows you to discriminate between certain mass profiles. And this is at the end what we're trying to do with the mass sheet degeneracy. So with the mass sheet degeneracy, you don't have necessarily a difference such pronounced as between a composite and a Palomar profile. So the differences by adding a mass sheet are much more minuscule, but it gives you a sense of the capabilities of what 2D stellar kinematics bring to the table. And what this is basically the figure of interest. So what you see here are, if you go through all this modeling process, what you see here is basically the constraints on d delta t versus dd. And what you see is basically that by means of stellar kinematic data, you can really start discriminating between various mass profiles and various inferred time delay distances. And 2D stellar kinematics really help in further narrowing down your PDF for both the time delay distance and the lens distance. And in particular for the lens distance, as you can see on the right-hand side. So this really brings an improvement of a factor of 5 to 6 to the table, and compared to single stellar velocity dispersions as those used in the literature. And now if you do the same exercise now with a mass sheet, because this is what we're aiming for, we're introducing this whole degeneracy of the mass sheet, which brings this whole degeneracy between the mass sheet and the inferred H0 values. And now we want to assess how much the stellar kinematics can improve on that. And what you see here in the middle panel in d delta t versus lambda, so lambda is the strength of the mass sheet, and d delta t is the time delay distance. In gray, you see the full degeneracy for the lensing only models, and in orange and blue, that's with the kinematic data, but for different noise realizations. So you really see from the PDF, whereas the constraints on lambda and d delta t are flat, from the histograms, the kinematic data really helps in discriminating or in further constraining the amount of mass sheet or the deviation from the actual true mass profile that can be added basically by means of such an elusive mass sheet. So basically the models really constrain this, and they limit contribution to the uncertainties of the time delay distance and the lens distance to the 10% level and 2% level respectively. And finally, if you basically have these constraints on the lens distance and the time delay distance, you can start crunching these numbers and turn it into a cosmographic forecast, which we did here for flat lambda CDM. And what you see here basically is the green is the marginalized over d delta t, so that is effectively more or less lensing only models. So these are the constraints for H0 and omega m. If you to some degree would neglect the kinematic data, then the red one are your constraints coming from the marginalized DD constraints, and the ideal one, which I don't show here in this panel, but only in the histograms, that's basically your joint inference for H0 and omega m based on the available lensing observations, and if you add to that JWST-like stellar kinematics. So in the end, what we predict is basically that all the precision that got somehow lost along the way by incorporating this full degeneracy due to the mass sheet degeneracy, a lot of this loss in precision basically can be gained back, such that we can achieve something like a 3, 4 to 5% precision measurement on H0 based on a single lens. So if you do this for the holy cow base sample consisting of 6 lenses, you might be able to constrain H0 with strong lensing to the less than 2% level probably in the near future, assuming that you have similar that you have kinematic maps of similar quality for these lenses. So I've already extended my time, so I'm sorry for that. I'll leave you with this, with the summary, and take any questions that you have.
Thank you, Akin. We're a little bit late, so if you have questions, please ask questions to Akin or the comments.
I have one question, Claudio.
Yes, please.
Akin, how many data do you wait from the James Webb Space Telescope for time delay cosmography?
So this is just one example, Mimosa. So the reason we went for this particular galaxy is because it's the brightest, it's nearest galaxy, it's the brightest galaxy, and it has really small uncertainties for the time delays, so 1.6%. So which basically gives you a floor of the best precision to be achieved. But you can do this for all the holy cow base sample. So if you're granted time from JWST, you can go ahead and apply this method to all the lenses. Of course, the quality of the kinematic data will suffer a bit depending on which target you observe, because some are further away, some are less bright. But on average, if you get something of the same order of magnitude, so kinematic data really spatial resolve, because all these things, these are individual, kinematic measurements as opposed to a single aperture stuff. So even I would say, even if it's like half the quality of this one, if you get this for the 6 lenses, I'm pretty sure that that we can significantly shrink the uncertainties based on the whole sample to something better than 3% at least.
And you need about 7 hours per lens, you were saying, right?
For this particular galaxy, yes, Claudio, 7 hours. For other, it really depends on what kind of quality you're aiming for. If you're aiming for the same quality for a lens, for a lens that is further away and less bright, then you might need 10 hours. But again, as I said, you might get away with half the quality. So 7 hours across all the 6 lenses might be feasible.
Okay, thank you. Thanks again.
Thank you.
We have to move to our next speaker. So Luis, can you share your screen? We are gonna listen to your talk, A Tale of Two Double Quasars, Hubble Constant, Tension, or Biases. Please go ahead when you're ready.
Okay, good afternoon, everybody. In this talk, we present a preliminary time delay cosmography from 2 double quasars in the Glendama sample. The Glendama project is aimed to accurately study a sample of 10 gravitational lens quasars in the northern hemisphere over a period of about 25 years, basically covering the first quarter of this century. The sample includes 7 double quasars with 2 images, A and B, and 3 quarks having 4 quasar images that we call A, B, C, D. The Gran Telescopio Canarias, GTC, is being used to obtain deep spectroscopy of the lens systems, while the optical variability of quasar images is traced from light caps, mainly based on observations with the Liverpool Robotic Telescope. These optical light caps allow us to measure time delays within images of 7 quasar images, of 7 systems, and see the results highlighted in blue in this table. Current Glendama delays have been estimated to a typical accuracy of 5%, but there are 2 exceptions. The relative error in the time delay of 0957 is well below 5%, and the 3 independent time delays of the quad 1413 have lapsed uncertainties. For a flat lambda CDM standard cosmology, for a flat cold dark matter standard cosmology, a small sample of gravitational lens quasars with measured time delays has recently provided a value of the Hubble constant in agreement with data for supernovae, but in tension with the planned flat lambda CDM result. It is also worth noting that Friedman obtained an intermediate result. Using 6 lens quasars, the Holy Cow collaboration found that H0 is within a range of 71.5 to 75 in standard units, in good agreement with the 1 sigma interval from supernovae data. However, the planned observations of the cosmic microwave background suggested a narrow range between 66.9 and 67.9, which is clearly inconsistent with length and supernovae data. The big question is whether this tension is due to possible systematic errors in some methods or has a physical origin. And in this talk, we use 2 double quasars of the Glendama sample, 0909 and 1339, to discuss the Hubble constant in a standard cosmology. The time delay between 2 images of a double quasar can be expressed in terms of the time delay distance, the speed of light, and a dimensionless multiplicative factor that we call tau AB. The time delay distance depends on the source and length redshifts and is proportional to the inverse of the Hubble constant. There is also a weak dependence on other cosmological parameters. I mean the matter and dark density and dark energy densities. In addition, the lensing mass distribution determines the multiplicative factor tau AB. Tau AB depends on the 2-dimensional position of the quasar images and the source quasar, and the lens potential and the positions of A and B. To realistically describe the lensing mass, we cannot consider a toy model such as surface mass density with circular symmetry, and our lens model consists of an elliptical surface mass density to represent the main lens galaxy, and an external share due to the gravitational action of other galaxies around the lens system. From the lens model, we derive the tau AB factor, and then a value of the Hubble constant can be estimated by measuring the time delay between both quasar images. This estimate is called H0 model. If galaxies other than G intersect the line of sight of the source quasar, we have to account for an external convergence kappa that finally decreases H0 in a factor 1 minus kappa. Our analysis focuses on the role that several observational model constraints play in estimating H0 model, and more precisely, the influence on the astrometry, the time delay, and the mass model of the main deflector. We show how changes in these constraints modify the accuracy and produce biases in H0. First, using 9 observational constraints and 2 observationally motivated priors for 0909, and assuming a singular isothermal distribution to describe the surface mass density of the galaxy, we obtain a value of the Hubble constant equal to 68.4 in a chi-square of about 10 to minus 5 that is consistent with 0. This best solution for H0 relies on the HST astrometry in the table 3 of LIHA and a measurement of the time delay to 6% precision from monitoring campaigns with the Liverpool telescope and the 1.55 meters telescope at the US Naval Observatory, and you can find the measurement in the slide number 1. We also use the lens model shower. The lens model shower allows us to fit the lens model parameters, the position and flux of the source, and the value of H0 for a standard cosmology. Unfortunately, the HST relative astrometry of LIHA positions of B and G with respect to A at the original coordinates is not so good as would be desirable. the errors in the position of B and G are relatively large, and this produces a broad valley in the chi-square curve. This produces a broad valley in the chi-square curve. So the constraint on H0 is very weak. Values below 55 and values above 80 are allowed. As we can see in the Castle's H-band frame of the lens system, the lens galaxy is very faint and the center is close to one of the quasar images, and the relative position was determined with a last uncertainty of 100 milliseconds in this case. If we were able to improve the LIHAS astrometry, decreasing errors of B and G in a factor 3 and 10, respectively, in a factor 3 and 10, the best solution of H0 would be practically the same, 68.4, 68.3, but its uncertainty will be dramatically decreased to about 10%, sorry. Therefore, our analysis of the HST frames of Q0909 might produce a better astrometry for the system, and this provides a measure of the Hubble constant to 10% precision. And this is a promising task that we and other astronomers are exploring. For example, the Cosmographic collaboration, and collaborators have reanalyzed the HST frames, obtaining an apparently improved astrometry and even details on the structure of the main lensing galaxy. For example, the error in the relative position of the galaxy was only 3 milliseconds, about 40 times smaller than the uncertainty derived by LIHA and by the Castle's collaboration, by LIHA and co-workers. Here we consider these new constraints to measure H0. Unfortunately, the best solution for H0, and the 1 sigma interval indicate that we are using biased data, leading to a biased result for the Hubble constant, a biased result of about 40. The new priors, the new parameter limits that we use in this fit on the structure of the galaxy don't play a critical role, because the use of previous priors also produce a value H0 below 50. Hence, the astrometry is biased. This is our main conclusion. The astrometry is biased, and an additional data analysis is required to estimate H0 to a precision of 10% in a reliable way. Regarding the double quasar 1339, we initially focused on 9 observational constraints: the positions of the quasar images and G, microlensing and extinction-free flashes of the quasar images, and an all-time delay of about 12% precision. In this case, we use an all-time delay in order to check the influence of the accuracy in the time delay on the determination of the Hubble constant. And also, we also use 2 observationally motivated priors on the structure of G, and consider again a singular isothermal ellipsoid. The lens model shower gives a very broad interval for H0, which is roughly ranging from 60 to 80. The observational constraint on the time delay is the primary contribution to the chi-square curve. We see that the red line corresponds to the chi-square, the contribution to the chi-square by the time delay constraint. And while other constraints, for example, the position of the galaxy, see the green line, play a secondary role. In a second approach, we use the new LT time delay, the new Liverpool telescope time delay, with a 4% error that has been presented in the slide number 1. And this leads to an accurate estimate of the Hubble constant, 67.8 plus minus 4.4. Now the chi-square curve is mainly associated with the observational constraints on the time delay and the position of G, the red and green lines. In a third approach, we again consider the new LT time delay and add a new prior. We use 3 priors instead of 2 because we want to fit a Debocles mass profile. Now we assume that light trace mass and consider a Debocles mass profile. And in this case, we use the effective radius, the ellipticity, and position angle for a Debocles light distribution in order to constrain the mass distribution. Our new scheme produces a bias H0 of about 100. Even the 2 sigma lower limit is above 85. The conclusion is that light doesn't trace mass, and isothermal or almost isothermal mass distributions are favored. The isothermal distribution is consistent with stellar and gas motions in the Milky Way, as you know, as well as observations of many galaxies. However, small deviations from the isothermal power law index, alpha equal 1, are plausible, and these deviations increase the error in the Hubble constant. The 6.5 error is probably not the total uncertainty. This initial error is probably underestimated. Well, our analysis of 2 double quasars suggests that a H0 model in a standard cosmology may be estimated to an accuracy of about 10%, and its 1 sigma interval is not in tension with other recent measurements from length quasars, supernovae, and the cosmic microwave background. It is also noteworthy that the central value of H0 model is of about 68, and this central value coincides with the upper limit of the Planck collaboration. And additionally, there is no clear way to increase the central value because a possible external convergence in one of both length systems would lead to H0 less than 68. Thank you for your attention. That's all.
Please, thanks. Any questions or comments?
Maybe one small question. I would like to, I am interested to know your opinion why there is, let's say, some divergence between other time delayed results and yours.
Or yes, for example, the results for Holy Cow, for the Holy Cow collaboration, are in good agreement with a larger value for the Hubble constant. Okay, but I think that perhaps there is a bias. I don't know if there is a bias or not in other results, but our preliminary, I remark this objective preliminary results suggest that the time delays of 2 length quasars in our sample are consistent with data of the cosmic microwave background. Okay.
How will you? Sorry, somebody was speaking.
Perhaps we have a bias in our analysis. I'm not sure because these are preliminary results, but in principle, I think that the main reason for the discrepancy could be the error that is assumed. Perhaps instead of a very short error, a very small error, the true uncertainty is about 10%. Okay.
Have you addressed the problem of the external convergence? Like, have you tried to estimate what is that effect in your 2 systems?
Yes, we went to check to change this. We went to do cosmography with several systems, not only 2. In principle, 7 or 8 systems, but in this preliminary analysis, we only have results for 2 of them. Okay.
Sherry, please. I don't know, can you unmute your microphone? Yes, I think so.
Hi, Luis. Thanks for the talk. I noticed in your mass model, you have assumed that the galaxy is isothermal.
Yes.
So the thing is, for the H0 inference, the H0 is actually quite sensitive to the radial slope profile. So if you have a mass distribution, there is some intrinsic scatter in the radial profile slope. Have you considered constraining the slope with either extended images of the host galaxy or from stellar kinematics?
Yeah, we think that an isothermal profile is a very simple description. Perhaps we need to consider different power laws, as I commented in the slide number 10. An isothermal profile could be modified towards an quasi-isothermal profile. So alpha could vary, for example, between 0.8 and 1.2. So if we consider this modification in the power law index, probably the error in the Hubble constant is larger. Instead of 6.5%, is 10% or 12%. But I think that this is a limit that we cannot improve for that double quasar, because for that double quasar the number of constraints is relatively small, and it's very difficult to improve an error of about 10%.
Yeah, I think you would need to get deep images, Hubble images or AO images that reveal the host galaxy of the quasars to provide more model constraints or with stellar kinematics. But thanks for the clarification.
Perhaps it's possible, thanks.
Thank you. Thanks, Luis, again. Should probably switch to our next speaker, is Eric Jullo. He's going to tell us about cosmography with space-based strong lensing observation. Yes.
Hello.
Hi.
So, all good? It's all good? Yeah, you see me? Good. Okay, so I'm going to switch a bit to another type of constraints on cosmological parameters, so from H0 to omega matter and WX. So first of all, I would like to thank the organizer for inviting me to give this talk. It's a great pleasure to be here with you. And right, so I'm Eric Jullo, and I'm coming from Marseille, from the Laboratoire d'Astrophysique de Marseille. And I've been working on this topic for many years, and I try to move the topic forward, although sometimes I lack some resources and people to help on, but I've seen that there are colleagues abroad that are pushing it forward, so it's good to know. So I think this talk will be more on the historical side and present some techniques that are involved rather than on very new results. Okay, so first of all, I will quickly talk about dark energy just to make sure we are on the same basis. Then I will describe some strong lensing models, because as for the galaxies scale models, it's important to have a good knowledge of the model, because the errors in the cosmography lies into the details. Then I will move to the cosmography that we have obtained so far, that I know of. And finally, I will conclude with some future prospects and work we are doing with space, preparing space missions like Euclid, for instance. Okay, so regarding the dark energy, so you all probably know that we are living in an accelerating expansion universe, and that there is about 68% of dark energy, and that dark energy explains, is used to explain this recent acceleration of the expansion. Also, it explains the slowdown of the formation of cosmological structures. Here are some quick plots to show you the behavior. Of course, most of you probably know it, but yeah, you have this on the left side, you have different behaviors of the expansion of the universe depending on the type of cosmology. So if you have a lambda CDMA closed universe, then you have these black curves. If you have a flat universe, then you have this blue curve, is the steady state expansion. And if you have a red curve, we are in a closed universe with a big crush type universe. And on the right side, you have the evolution of dark energy as in a green line, depending on this W parameter, which is the equation of state of dark energy. And right now, most of the measurements find that Wx is estimated to be about -1. So there is a constant density of dark energy as a function of redshift compared to the density of matter, which is changing with redshift. You see, as the universe grows, the density decreases. So here is a kind of busy plot that illustrates the state of the art of dark energy measurements. So you have the well-known Planck measurement in black and in green for this on the left side. And on the left, you have the dark energy survey measurements in gray. And when you combine with the BAO measurement, you obtain the orange curve, and the combination is in purple. And when you see there is a 1.5 discrepancy with the estimate of S8 parameter with respect to Planck. And when you look on the kids side, then you have a larger discrepancy, like 3 sigma discrepancy, mostly due to the shear measurements, so the cosmic shear measurements, and which are kind of slower. You see that the blue lines are identifying the limits on the death side, and you see that the kids' measurements are slightly lower. Also, you can notice that the precision on omega matter is almost 3 times smaller on the death side than on the kids' side. So there are still some discrepancies that are being investigated by the 2 collaborations. Okay, so this was for dark energy. Now let's move on to galaxy cluster and strong lensing. So how does that work? So you have this well-known benchmark where you have the background source and you are the observer on the left side, and you see multiple images lensed by this cluster of galaxy. And you have this deflection angle, which is the central quantity in this analysis, which is depending on the ratio of distances, which contains the cosmological information, and the gradient of the potential, which is related to the mass distribution in the lens. And here you see the relation of the estimate of the distances, and this is the Poisson equation, which relates the potential to the matter density. So on the external side of the lens, you have the weak lensing, and on the central side, you have the strong lensing. So we deal with clusters, so it's important to know what the galaxy cluster is made of. So it's mostly made of dark matter, 80%. Then you have in this illustration of the bullet cluster, you see the bow shape of the interaction of the plasma when the 2 clusters collide together, and this is 15% of hot gas. And then you have the stars and inside the galaxies, which account mostly for 5% of the total budget of matter. And you have different observables that allow you to quantify these different quantities. So in the rest of this talk, I will focus mostly on the strong lensing side. How do you identify multiple images? Well, then you have this type of images from HST, for instance, and you observe these giant arcs and these multiple images. And what you want is to make all these multiple images reconstructed into one single source. So how do you do that? Well, you have this different methods. I would say there are the physically motivated methods, which are based on analytical profiles motivated by simulations. And you have the agnostic grid-based models, which do not want to make some assumption on the model, and then they use like a distribution of potential over the field of view. And in the end, well, everything is described in terms of potential, and you have the large-scale smooth components that we call the potential of the cluster in red, for instance, in this figure. And you have the galaxy scale components in purple. So we are using this tool, lens tool, that we've been developing for years now to do this type of analysis. So here is an illustration of the usual profiles that we explore in our lens tool code. And then, as I said before, you need to identify cluster member galaxies to model properly the matter distribution. So what you do is usually you do a color magnitude diagram and you observe this red sequence where all the cluster member galaxies reside. So you pick them. And you say, or you assume that these galaxies, and this has been known for years already, follow these either Fiber-Jackson and Cormendy relations as a function of size and brightness, or velocity and absolute magnitude. So you end up with this equation when you do these assumptions, which relate the velocity dispersion of the galaxies as a function of their luminosity and their size, so the cut radius in the previously displayed PIMD model. So the cut radius as a function of luminosity. And you assume that all the galaxies in the cluster have the same formation history, and therefore they can follow the same relation with these scaling parameters, sigma star and Arcot star. And you can see that in this paper, Vermeer et al. 2019, that I will cite a couple of times because I think it's an important paper, there are 3 clusters that have been adjusted with this model, and they all have the same Arcot, sigma 0 and Arcot 0 star. These are the same stuff, parameters. And this is very encouraging for the analysis of galaxy clusters, because this is a critical unknown. I will come back to this later. Okay, so now when you have your cluster models, then you have this type of constraints. So you can either do a source plane fit, where you put all your images back to the source plane and you compute the barycenter of the source positions and you measure the distance between the source position and the barycenter. This is the source plane fit, and this is quite quick. But sometimes it becomes inaccurate, and then you want to move to the image plane fit, which is slower because it requires an iterative search for the multiple counter images. Sorry. And well, this here is the proper chi-square where between the observed and the predicted position of the arcs for each individual galaxy. So this is the way it works. Now, how do we do cosmography? Well, cosmography resides in the first great ratio of distances here for the deflection angle. And you see that if you have galaxies at different redshift, well, if they are at low redshift, they are like closer to the center. And if they usually are higher redshift, they are farther away from the center. And this is the dependency of this efficiency ratio on terms of cosmography and in terms of cosmological parameters. So you see here, if you change in your estimate of the efficiency ratio, the W parameter, then you increase the value here on the knee of this curve, you see? So you have constraints around this redshift for a cluster at redshift 0.2, and you can have good constraint on WX. On the contrary, if you want to constrain better omega matter, you see that you better constrain it on the high redshift side, and then you use constraint on the higher redshift, at higher redshift to constrain the omega matter. In reality, you have constrained both on low redshift and high redshift, so you constrain both effects. So in the analysis I did in 2010, so I used this galaxy cluster, about 1689, and you have plenty of observations lasting. So it has been observed for more than 6 years before we can do this analysis. So we required many spectroscopic redshift for the sources and many, of course, multiple images. At the time, this was the best known cluster. And here are the constraints that you've probably seen already. So these are the comparison between constraint on the strong lensing in orange and the supernovae at the time, and the X-ray and the Planck, supernovae measurements at the time. And you can see the combination of these three constraints gave orthogonal constraints and precise measurements. And later, we were happy to see that Gabriel Camini also found good constraints on Hubble S1063 with the similar technique. And yeah, it was nice to see that, that it could work again. And just to mention that this measurement requires long pre-processing to identify strong lensing outliers and estimate model uncertainties, and I will come back to that later. Of course, then once you have a model that works, you want to test many models of modified and dark energy models. So this has been achieved by a colleague of mine in Chile, Juan Magaña, in 2 articles, and you see that you can constrain the deceleration particle for different models, and you will see here different constraints. So I would like to spend now a bit of time on some modeling uncertainties related to this galaxy cluster members. And you see that these galaxies, of course, they do not follow the same history, and they do not share the same exact scaling relation. And you see that if you introduce some scatter in the analysis, then you have some errors. And then it's important either to simulate this with simulations, to estimate this with simulations, or get a more complex model. Also, you can have some effect of the line of sight, but and it seems to be the same order of magnitude as the scaling scatter. Well, I would like to spend a few minutes on this also. You can see in Limousin et al. 2016 that you can also have different models which give the same exact RMS. And it's impossible to go further without doing some more advanced modeling. So this is what has been done by Kawamata et al. In 2016. But then you end up with clumps of matter a bit everywhere and external shears that it's hard to understand the physical meaning of it. And in 2 papers, it has been guessed that this could be related to the plane of the sky or line of sight over densities. In fact, in a paper that by Anna Sebron in 2017, we also investigate this and found that this galaxy in the outskirts could also impact the reconstruction. So there are comparisons, of course, more and more with simulations, and I think this is the way forward. And you see that if you do it properly, you manage to recover the agreement with the observations. But on the other side, there are also some other observations, like the probability of observing strong lensing in galaxy clusters, which find a factor of 10 discrepancy between simulation and observation. So this is still a debated issue, and eventually there is some answer on on the simulation side. So finally, I would like to conclude on some work that we have been doing in Euclid. So here is a challenge that we conducted in in 2016 with Ben Metcalfe, and we simulated 100,000 strong lenses, both for kids-like and Euclid-like images. There were 24 participants and many techniques, mostly based on neural networks. And you can see that it's easier to find. So I don't want to spend time on this technique because I don't have time, but you can see that it's more difficult to find good lenses with space-based images than with ground-based images because the colors help a lot. So even if you have high quality images, it's not sufficient to find multiple images. So I think this was the conclusion for this exercise. And currently, right now, there is a challenge going on in Euclid. So this is what we call the 8th scientific challenge, challenge 8. And this is a very new image of the result of simulation, where you have this image here of the strong lensing arc and some color images also that will be used then to train the neural networks. Also, on the Chinese side, there are some activities in this respect, and we have been working with a master student to see the how to choose 6 clusters that give best constraints on this WX and omega matter plane. And you can see that by choosing clusters well distributed in redshift, you get orthogonal constraints to get better precisions. There are also some proposals now to measure some to follow up these galaxies in spectroscopy. So in Colette et al, it was expected to find 170,000 lenses in Euclid and 120,000 in LSST. And so in DESI, right now, we are already able to observe some spectroscopy from some arcs. We expect to find about 400 spectroscopic redshift for multiple images. And there is the big foremost proposal, which is expecting to find 10,000 spectroscopic redshift, but we will know the decision of the TAC only by December 2021. Okay, so here is my conclusion. So gravitational lensing of cluster can test dark energy models. Currently, we are limited by systematic errors, but recent hydrosimulation will help to constrain these models and understand better the evolution of galaxies in cluster. And meanwhile, we are preparing observations and to analyze the data.
Thank you. Thanks, Eric. Questions for Eric? Anybody, participants or speakers? Well, I have a question. So according to your conclusions, do you think that the bottleneck in order to make progress in cosmographic analysis with clusters is the modeling? So we are limited by the uncertainties in the mass models of the clusters, or do you think we need more data on this same cluster? So we need velocity dispersions, we need more multiple images, we need more redshifts. What do you think we should improve on?
Both, of course. So we, as usual, we do as we do with what we have in hand, you know, right now. So I think now there is a lot of news data that we can use to measure velocity dispersions. This has been demonstrated as a way forward. I must admit that before news, we were a bit stuck in the analysis because of this. So it seems to me that this velocity dispersion is very very strong new constraints. It seems to me like a bit the same as for the H0 measurements. Velocity dispersion will help a lot. Also, there are many simulations, work on simulations that are going on, and it helps to compare data with simulations or results with simulations, but it's not a trivial exercise. And there are many papers that were contradictory in this respect in the past years. And yeah, then once we try to match the best we can, the data and the simulations, you know, sometimes you have to reproduce exactly your data with the simulations. Then you start to find that it works, you know, but it's not a trivial exercise. And yeah, of course, on the data side, yeah, the more data we have, the better. If we can use the velocity dispersion of the stars inside the galaxies, but also now that we have a lot of spectroscopy coming from massive spectroscopic surveys of the galaxies inside clusters, we can also estimate the velocity dispersion of the galaxies inside the cluster and get some estimate of the mass. We can also combine with X-ray measurements. You know, we have plenty of data now that can be combined to make this analysis.
Thank you. Gabriel, I see.
Yes, it's just actually a curiosity. In that predictions for the Chinese Space Telescope, you have,
yeah,
I know they might be simple predictions, but you have a cluster at redshift of 2. I mean, in terms of multiple images in background sources, what kind of redshift distribution of the background sources you expect for such high redshift clusters? Because I imagine you have much higher background galaxies and it'll be kind of very challenging to obtain the redshift of.
Okay, whatever. So yeah, you know, these observations, they will go down to magnitude about 29, 30.
Mm-hmm.
So they basically, to do these simulations, we use the Hubble deep field simulations, and yeah, even at redshift 1.5, you find a few arcs. Well, of course, it's these are very simulated, very simple simulations. It was just a master studies project, so we didn't go very far, but still, I thought it was interesting to see these orthogonal constraints. And again, yeah, to have multiple clusters distributed in redshift, I think this was the point then. Exactly, the cluster is not maybe completely decided yet. It will depend on other aspects of the mission.
Okay, thanks.
Piero?
Yes, thanks, Eric, for the nice overview. One question, so since, I mean, given the increasing quality and number of constraints, right, the number of multiple images, velocity dispersion, and so on, do you think it would make sense to invest on expanding the current lensing software? You know, perhaps Lens Tool, you know, was developed 20 years ago. Well, yeah, almost 20 years ago when the data were different. What do you think? Can this be a limitation to the objectives that you laid out?
Well, I must admit that every time I see a new paper with a new code coming out, I feel a bit ashamed not having worked more on Lens Tool. Huh? Because yeah, I'm busy with other commitments, and I cannot find a moment to improve Lens Tool more. But I have plenty of ideas. But yeah, well, anyway, people do not wait for me or for us to work on Lens Tool, and they do their own stuff, and it's very great. So yeah, we will see. This is how it works. But yeah, for sure, the tools are coming. So
okay,
it's always important to have new tools, as we said before. Having new tools allows you to handle better the new data.
Good. Thanks, Eric, again. We can go to our next speaker. Our next speaker is Sherry Suyu. And Sherry is going to tell us about cosmology and stellar physics with strong lensing.
I need to stop here.
Yes, please.
Okay, I'm going to share my screen. Can you see the full screen?
Yes.
Okay. Hi, everyone. So first, I would like to thank the organizers, Claudio and Mimosa, for having me here and for organizing the session. So we've heard earlier in the session on cosmology with lens quasars. In this talk, I will tell you another type of lens transients, particularly lens supernovae, and how they can be used for cosmology and stellar physics. So here is a quick animation showing the lens supernova event. So on the left, we have a supernova host galaxy, and we are on Earth on the right. And when a supernova goes off in the background host galaxy, what we will see essentially is multiple images surrounding the foreground lens galaxy appearing at different times. And we have already seen earlier in this session how we can use such time delays between the multiple images for cosmography. So the idea goes back to Refstel in 1964. Just very quickly, so the time delays is related to this time delay distance that is inversely proportional to the Hubble constant, and the Fermat potential that's related to the mass distribution. So as we've heard in the first three talks, essentially with a time delay and a mass model, we can infer this time delay distance and then infer the Hubble constant. The time delays from strong lensing doesn't allow us just to do cosmology. It actually allows us to probe the progenitors of type 1a supernovae. So despite decades of studies, the progenitors of type 1a supernovae is still unclear. So the two classical scenarios are on the left, single degenerate system where we have a white dwarf accreting material from a non-degenerate companion. And as the white dwarf approaches the Chandra-Sekhar mass limit, it explodes. Or you have the double degenerate scenario where you have two white dwarfs merging. Or it could be a mix of these two mechanisms or some other mechanism such as double detonation. And it turns out strong lensing really helps you in probing the progenitor system because strongly lensed supernovae will allow you to observe the very early phase light curves and spectra of supernovae to constrain the progenitor scenario. So the idea is that we can detect a lens supernova system based on the first appearing image, predict when the next ones are going to happen, and then we can observe the very early phase observation of a supernova, and that provides information regarding the progenitor scenario, whether it has a companion regular star or it's a companion white dwarf or something else. Observationally, it took 50 years to observe the very first lens supernova event after Refstel first envisioned this phenomenon in 1964. So in 2014, Pat Kelly and collaborators discovered the first lens supernova with spatially resolved multiple images by from Hubble Space Telescope imaging campaigns from the Hubble Frontier Fields and from the GLASS survey. And this supernova was named Supernova Refstel in honor of Refstel. So on the left is a Hubble imaging of the cluster. And these blobs, as you saw, similar to what Eric showed, these are the galaxies in the foreground galaxy cluster. And behind the galaxy cluster is a spiral galaxy that is strongly lensed into 3 images with one on the top left, on the zoom on the top right, you can see. Second one here in the middle with a zoom in the right middle panel, and then bottom one on here on the bottom with a zoom on the bottom right. And by chance, a cluster member, so a cluster galaxy in the foreground lies on top of the spiral arm of this spiral image in the bottom, further lensing the spiral arm into multiple images. And by chance, a supernova went off in that exact same spiral arm, and it was caught by HST imaging. And you can see the 4 images, S1, S2, S3, S4 of the lens supernova Refstal. So when this event happened in 2014, there was a huge amount of excitement, as you might remember. And the key question is, when will the other 2 images appear? So there's the second image, which I'll call SX, and third image SY. So from the preliminary mass model from the discovery team, SY is actually appearing before image S1. So, and there is no image data taken of this cluster like 15 years before. So basically SY is not observable. Nonetheless, SX should happen after S1. And this is where it's really exciting, as many teams then try to predict better when SX is going to reappear. So Claudio, our session chair, has acquired at that time director's discretionary time from ESO to use the then MUSE instrument to get basically spectra of many of the galaxies in the field of view, which helps to cleanly separate what are the foreground lens galaxies and what are the background sources. And the spectroscopic data was then shared with many teams. And shown here now is the prediction of the reappearance of image SX relative to S1 in terms of the brightness, so magnification ratio in the y-axis. And then in the x-axis is the time delay of SX relative to S1. So the different symbols here are the predictions from the different teams using different data sets, either a gold sample or the whole spectroscopic sample. And from this prediction, this is really a true blind test in that all the teams basically predicted in October 2015 these predictions before SX reappeared. And most of the teams actually predicted that the SX image should reappear before the end of 2015. And long and behold, at the end of 2015, the image SX did reappear. And on the top, this is the image taken in December 2015 relative to the image taken in April earlier in this year. And if you focus on where the circle is, you see that in December on the top image, there's a little image of supernova image SX that reappeared, which was not there earlier in the year. And given that single detection, we can then have a constraint on the brightness and the time delay of SX shown by the 1 and 2 sigma contours. And two teams did particularly well. One is led by Masamune Ogiri in Japan, and the other team was led by Claudio in the red. And I would like to note that this prediction was actually done with GLEE, which is a software that Alexi Hakala and I have developed. And this is the same software that actually has been used in Holy Cow for time delay cosmography. So our successful prediction of the reappearance of supernova Refstal demonstrates the robustness of our modeling approach and also on the software itself. Now, we didn't just predict the brightness and the time delay, we could also predict the location. And you can see here the different circles are the predicted locations from the different modeling teams. So Claudio's team is marked here in green by Grillo, and the size of the circle was the estimated 1 sigma uncertainty from the model predictions. And when image SX reappeared, it actually was located at where the red cross you can see, and notice this is 2 arcseconds on the sky. So we were able to predict the reappearance of image SX with better than 0.2 arcseconds. Now that image SX has reappeared, the Supernova team has been busy monitoring the system, and I heard Pat Kelly and collaborators actually have a forthcoming publication on the measurement of the time delays. So in the meantime, before the publication is out, Claudio Grillo, Piero Rosati, other collaborators, and myself, we performed a feasibility study to see how well we can use supernova Refstal for H0 measurement. Essentially, the question is how well can we actually model this complicated cluster mass distribution for precision cosmology? So we have used the delays measured between the four S1, S2, S4, so the 4 short delay images, and then an estimated delay of the image SX based on that single detection in Pat Kelly's paper. And on the right, you can see basically the probability distribution of the Hubble constant from our mass models that incorporates all these various systematics that we can think of, assuming a time delay of 345 days. And actually, in the end, it's this time delay of SX that's going to determine the H0, at least the centroid, because the value of SX delays can shift the centroid values. But nonetheless, the estimated precision, currently including all the known systematics, is actually on the order of 6 to 7% from the single cluster, so which is very promising. So we are eagerly waiting right now for the time delay measurements from Pat Kelly in collaboration. And since Supernova Refstyle, there has been now 2 more lens supernova event. The one on the left here, this is a galaxy scale lens supernova that was discovered by Arul Gubar and collaborators in the IPTF survey. So this is the intermediate Palomar transient factory. And this system was particularly exciting because the supernova here is a type 1a, which is a cosmological probe, in contrast to Supernova Refstyle, which is a type 2 supernovae. And very recently, as you might have seen on the archive just a few weeks ago, Steve Rodney detected another lens supernova in this spectacular galaxy cluster. And the supernova is named Supernova Requiem. So the supernova images are here. You can see the red and purple images that was visible in the 2016 image of Hubble, but then when they retook an image in 2019, these point sources were no longer there. So unfortunately, we can't follow up these 3 supernova images. But from that single epoch, Steve Rodney and collaborators can estimate the time delays based on the different supernova colors. And there is a predicted 4th image that should come about in 2037. So a bit, we have to be a bit patient for seeing that image. Nonetheless, these lens supernova systems have demonstrated that lens supernova have become a reality. And given that, our research group in Munich have started a new research program called Holy Smokes. So Holy Smokes stands for Highly Optimized Lensing Investigations of Supernovae, Microlensing Objects, and Kinematics of Ellipticals and Spirals. This is funded by the European Research Council. And here are the Holy Smokers, who I owe many of my thanks to. And in particular, I'd like to highlight the junior people in Munich, as I will be showing the results of their work for the rest of my talk. So Jana Bayer is a master's student, and Simon Huber, Stefan Schultz are PhD students. Raoul Canameras, Stefan Taubenberger, Christian Vogel, and Akun Yildirim are postdoctoral fellows. So one of the things we first looked at is how well can we actually measure H0 from a future sample of lens type 1a supernova from, for example, the Rubin Observatory Legacy Survey of Space and Time, LSST. So we expect about 20 lens type 1a supernova from LSST, which we can have precise and accurate time delay measurements. And here is the redshift distributions for the lenses, deflectors, and in the x-axis, and the source redshifts in the y-axis for these 20 lens supernovae, and assuming that for each of these systems, we can get the necessary ancillary follow-up, such as the monitoring and the high resolution imaging. We estimate we can measure the distance, time delay distance, and the angular diameter to the lens with about 5% uncertainty. And with those assumptions, we forecast that we can obtain H0 with 1.3% precision and flat lambda CDM from this sample of lenses. Now, the challenge, of course, is to find these very rare events. So ultimately, it's going to come from LSST. But fortunately, even now, we can already start to do the search in the Zwicky Transient Facility, so ZTF. So ZTF has a very wide field of view camera, as you can see here in the middle, that's much bigger than all the other surveys. So with such a wide field of view, it can efficiently scan basically the northern sky every 2 to 3 nights. And from the ZTF, we can essentially get alerts or transients that happen. So from ZTF, we can find supernovae, but we can't really detect whether or not these supernovae are strongly lensed or not from the survey in terms of seeing the multiple images, because ZTF doesn't have the spatial angular resolution given the pixel size is about 1 arcsecond. Therefore, we combine ZTF with pan-stars, where pan-stars has a higher angular resolution, but not the time domain information. And so we combine the time domain from ZTF, higher angular resolution images from pan-stars to search for lens supernovae. Essentially, our strategy is to find lens galaxies in pan-stars as potential hosts of supernovae. So we have used machine learning techniques, particularly convolutional neural network, as mentioned by Eric before. And we have applied the CNN convolutional neural network to the entire Pan-STAR 3Pi survey. And from that, we have found 330 new lens candidates. And here is a gallery of some of these new ones. So as you can see, most of these, you can see these visual arcs. They're all very promising. And actually a few is recovered real lens systems. Recently, we have improved our neural network approach. So building upon CNN, convolutional neural network, we actually use a residual neural network. And this actually allows us to reduce the false positive rate to about 0.01% from the 1% from the CNN. So by using ResNet with such a low false positive rate, we can actually apply this systematically to the HyperSupremeCam HSC public data release without much pre-selections on the catalog level. And by doing so, we actually obtain more than 400 lens candidates, and about 40 of which are newly discovered. And shown here are some of the new lens candidates that we have obtained from HSC. And these are the systems and the work led by Raul Canamares here. Now we essentially, from the HSC and the Pan-STAR survey, we just need to wait for one of them to explode in ZTF, but the chance of that occurring is actually quite low because ZTF is a rather shallow survey. So to really get lens supernovae, we need the Rubin Observatory Legacy Survey of Space and Time, LSST. So LSST is a high Étendue survey telescope. It's going to sweep the entire southern sky for every few nights for 10 years. And the expected start date is around 2023. From various studies and forecasts, we expect to have hundreds of lens supernovae in the 10-year LSST survey. And in the past couple of years, there's been a lot of discussion within the LSST project on the observing strategy. In particular, when, where, and which filter should we observe the southern sky? And this survey strategy should serve the wide range of science cases of LSST, ranging from solar system studies to stars in our Milky Way to extragalactic science and all the way to cosmology. And in particular, the cadence strategy will affect us in the sense that it will affect both the number and the time delay of lens supernova that we expect. So Simon Huber, who is a PhD student here, has taken on the challenge to quantitatively assess the impact of LSST observing strategies. And in particular, he has compared these 20 LSST observing strategies shown in the x-axis. So don't worry about these cryptic names, but basically these strategies are categorized into 3 categories: baseline-like in orange, higher cadence in pink, and higher cadence at the expense of fewer seasons in blue. And in the y-axis, I show here the number of lens supernova 1A with good time delay measurements, meaning time delays with better than 5% precision and 1% accuracy. So that's good enough for cosmology. And from the study, so the gray bars is just from LSST data alone, and the black is from LSST plus follow-up. And from this study, essentially, we can conclude that we should use LSST as a discovery machine and then obtain dedicated monitoring, because the dedicated monitoring will then allow us to measure the time delays more precisely and accurately. And also, we prefer observing strategies that have higher cadence, as that also give us a higher number of lens supernovae. So until recently, most of the time delay measurements have been done through photometric measurements, so from light curves. And this is where supernova can provide you more information because the spectra of supernova evolves over time. So the question is, can we use the spectra to measure time delays? And Jana Bayer has demonstrated this to be conclusively yes. So the idea is that you can obtain spectra, sequence of spectra for the first appearing image at different times. So this is shown in the spectra in the different colors. And as you can see, for example, the H alpha line, the wavelength of the line is increasing as a function of time. So then you can take a spectra of the trailing supernova image and compare to the spectra of the first image to see the phase, the relative phase, and from that get the time delays. And Jana has shown that you can actually measure delays with uncertainties of around 2 days for each spectral features, and you can improve on this with multiple spectral features and with multiple spectra. And finally, with lens supernova, as it's a short-lived transient, we need to be able to do the analysis quickly. So we have recently explored lens modeling through machine learning. This is inspired by the works of Yashar Hezaveh and Laurence Levasseur. So Stefan Schultz here has created a simulation pipeline to simulate realistic lenses, as you can see here, and then trained a neural network to infer the mass parameters of the lenses. And you can see here the recovered Einstein radius versus the input Einstein radius. You get mostly the good recovery, although there is some scatter in the predicted Einstein radius. So it's not as precise as the manual modeling, but the advantage here is that you can actually get the mass parameters within a fraction of a second. So what are the future prospects? Well, experiments and surveys in the 2020s, including Euclid, Rubin, and Roman observatories, will provide hundreds of lens supernovae. And you can see here the various surveys, and we will have JWST for high resolution imaging and spectroscopic follow-up. So the next years should be really exciting in terms of lens supernova studies. With that, I will summarize and conclude here. So lens supernovae provide great opportunities to constrain supernova progenitors and cosmology. Supernova ref style blind test demonstrated the robustness of our cluster mass modeling approach and the software GLEE. We've started a new program, holy smokes, on lens supernovae. We found more than 500 new lens candidates in Pan-STARRS and HSC that serve as a potential host of supernova. And in terms of LSST observing strategy, we're advocating for higher cadence and longer season or cumulative season length. We have developed new methods to measure time delays and also lens mass modeling through machine learning, which yields a huge gain in speed. Finally, current and future surveys will have hundreds of lens supernovae, making lens supernova a competitive probe of cosmology and supernova progenitors. Thank you very much for listening.
Thank you, Sherry. Questions for Sherry? I have a question. Oh, sorry.
Sorry. So, yeah, I will ask you the same question that have been asked to me.
Okay.
You handle so many tools in the community. How do you compare, or what is your opinion on this?
So I think we're entering a golden era for lensing, and that we will have really hundreds and thousands of lens systems that will be discovered. And in that sense, I think the conventional approaches that we have been using so far will kind of hit a bottleneck. This is either from your lens tool or from our software GLEE. It just takes too long to analyze them. And I think in that sense, the machine learning approach is really good in getting a crude first estimate. And while we're pushing the limit to see how well we can actually recover the true parameters, I think there's various progress on this front, and also from, for example, the work of G1 at Stanford. So I think this is worth exploring in order to just process these new lens systems or lens candidates quickly. And then from that, we can select the systems, like prune the big sample into a smaller sample for the specific lens science cases that we want to study. That's at least my current idea.
Okay, thank you.
More questions for Sherry? I have a question, Sherry. Do you have a probability distribution of the time delays of your predicted 20 type 1a supernovae, or of not of the delays of the Einstein radii or something related to that?
Yeah, so this 20 actually came from the investigation of Simon Huber. So essentially, this was the number expected from LSST where you would get good enough time delay. So precision's better than 5% and accuracy better than 1%. And that's why we sort of have this 20 from as like, it's still actually rather conservative. I think we will have more, but these are essentially the ones that you can have a longer time delay. Typically they have delays longer than 20 days so that you can get the accuracy and precision better than the 1% and 5% respectively. So there's many more actually. There's hundreds of lens supernova 1A expected, but most of them will be shorter time delays and therefore it's harder to measure the delays.
So they're almost all galaxy scale systems, right?
Yeah, these ones, yes, good point. So we only focus on galaxy scale systems. There are galaxy cluster systems as well. So this we haven't looked at, but so for example, Tanya Petrushevska have been looking at the rate of lens type 1A supernovae. And I mentioned this is only type 1As we've looked at. There's also type 2s that will have comparable numbers. So I think we should be able to do like at the 1% level, assuming systematics are under control.
Thank you. Okay, if there are no more questions for Sherry, thanks again, Sherry, and we can switch to Gabriel Caminian. And Gabriel is going to tell us about cluster strong lensing cosmography, robust cosmological constraints from a sample of galaxy clusters.
Yes, that's right. I guess you can see my slides, correct?
Yes, we do.
Okay, thank you. Yes, I'd like first to thank the organizers for the opportunity to be talking about my work here. And as Eric said before, with strong lensing, you can also measure other parameters like omega matter and the dark energy equation of state, in addition to the Hubble constant. And this is what I will be talking here. I will not be talking about time delays measurements, only constraints on this background cosmology using cluster strong lenses. Okay, just very quickly here, because this has been said before, in the strong lensing, we have the background galaxy that is multiple lensed into different images. And we can observe these images, that they are distorted, and can even identify multiple images from the same object. And what's interesting and important here is that this effect depends only on the total mass distribution of the clusters and also the relative positions of the observer, the lens, and the background galaxy that we observe. And with this, we can do a lot of different sciences. We can study the dark matter content in the clusters or in the galaxies. However, here my work focuses on galaxy cluster strong lensing. We can study the dark matter, the inner slope of the mass distribution, and the substructures. We can also constrain the background cosmology of the universe. When I say background cosmology, I'm referring to the cosmological parameters, the omega matter, the density of the dark matter plus standard matter, the curvature of the universe, and the equation of state for dark energy and its possible evolution with redshift. To do this, of course, we need good data, but we do have a lot of good data nowadays. Basically, high resolution photometry from HST, and okay. That has been observing a lot of clusters in different surveys, but we also need a lot of spectroscopic information, and the spectroscopic information is important because we have to have the spectroscope, the redshift measurements of these background galaxies, and also we have to have a good estimate of the cluster members in the lens plane. And of course, with this good data, we are basically free of misidentification of multiple images that has happened in the past. And we also break out of the degeneracies between the lens mass distribution and the redshift of the background sources. And the data, basically from photometry, we use HST that has been used extensively to observe galaxy clusters in different surveys. Basically, we have over 1,000 HST orbiters observing clusters, around 70 clusters in several different large programs, with, for example, with the CLASH survey, and after the Hubble frontier fields, observing very deeply a very small sample of clusters. And also the last surveys, the relics that observed 41 clusters with good HST imaging. And on the spectroscopic side, we have had efforts with basically CLASH validity with using slit spectroscopy, also using HST Grism spectroscopy. We have had GLASS. And what's basically changing the game now is what some people mentioned before is the multi-unit spectroscopic explorer at VLT ISO. And basically, we will be using this good data to constrain this cosmological parameters, omega matter, the curvature, and the equation of state of dark energy. And how those Erki has already explained this very nicely, but I just want to be quick here. This is the equation that a very simple equation that relates. This is the lens equation that relates the observed positions and the real position that we do not observe. It's unknown in the model, and also the deflection angle here, which is shown here. And basically, the dependency on the cosmology comes from the angular diameter distances between the lens and the background source, and also the observed between us and the lens and the background source. And in this equation here, we can see that it is this quantity here, it can be easily absorbed by the lens potential, which is related to the mass distribution of the cluster by just a multiplicative factor. But this happens if we have only one multiple image that we observe. However, in clusters, we are very lucky because we can easily observe several different multiple images from different background sources at different redshifts. So we have not only one lens equation, we have any lens equations, and basically for each lens equation, the lens potential is the same, but this quantity is different. So in this way, we can just break the degeneracy between the cosmology and the mass distribution of our lens of our cluster. Of course, this idea is not new. It has been explored in the past using the cluster Abell 1689, and this is again the figure from Eric Julot 2010, showing the constraints on the cosmological constraints coming from this cluster strong lensing, of course, using a lot of spectroscopy and very good photometric data. And here is the combination with different probes. Here in blue is CMB, and in red is BEO, if I remember correctly. And okay, but just going back to this, and then actually in reality, in the end, what we are sensitive here, we are our standard ruler, let's say, is the so-called family ratio, which is this quantity here, that is the ratio between the angular diameter distances, in this case, for these two background sources. And if you will look in some details of this quantity, I'm showing here for a specific cosmology. Here is the so-called Cpl Cosmology, where we have these three parameters. It's and we have the omega matter, the curvature, and two quantities that describes the equation of state of dark energy. It's one constant plus another constant times evolution with redshift. So basically, if the WA is 0, we have a constant equation of state, and if W0 is -1, we have the standard lambda CDM cosmology. And these are the isocontours of this quantity, just to illustrate. And this is what we expect as a degeneracy in our constraints when using this quantity to measure the cosmological parameters. And here, of course, I'm just excluding some values that are known physical for cosmology. And when we go to real data, now here is the result for Abell 1063. We obtain these constraints that they follow very nicely the expected degeneracies of this quantity of this family ratio. So it's a good result because it ensures us that we are in a very good direction in our strong lens model. And just to mention here that these constraints, they come from the strong lens modeling, and of course we are varying all the mass parameters together with the cosmology. Okay, but this is for only one cluster, and even in 2009, even before people start applying this to real clusters, some people, of course, studied the possibility of combining different clusters, combining this analysis on different clusters to better constraints, to basically reduce the systematics and the error bars on the cosmological parameters. And these are the results from a set of simulations. Here the authors use somehow idealized sample, but it's extremely informative, this figure here, where you have the gray contours are constraints from single clusters, single simulated clusters, and here in black you have the combined constraints, and showing that it might be possible to combine clusters. And what I'm going to talk now is about the cluster sample that we use it to do this joint constraint. And basically we are using these 5 clusters. These 5 clusters, they have a very detailed mass modeling, very good spectroscopic data from Muse, and also very good HST data from different surveys, from Clash and Frontier fields. And we and here is the redshift range of our lenses and the redshift range of our background sources. And each cluster has between 7 and 20 families of different sources at different redshifts. We use the parametric approach. We use the lens tool to model, and the strong lens model of the mass distribution is explaining in these 2 publications. And we need a relatively low number of free parameters to describe the mass distribution. And of course, we are adding on the top of these free parameters the cosmological parameters. And what we did systematically, we studied 4 different cosmological scenarios. One is a simple cosmology varying omega matter, but fixing the curvature, and also the dark energy equation of state to the standard value -1. And we have a flat cosmology, and we have a curved cosmology fixing the equation of state, and also we have the Cpl cosmology varying the 3 parameters, but fixing the curvature to 0. The results from these different clusters on the base omega matter cosmology is this. It's summarized in this figure here. What I'm showing you here is the PDF, is the posterior distribution of the parameter omega matter, and each color indicates a different cluster. And in gray here you have the combined cosmological constraints of these 5 clusters. And you have here the redshift of the cluster. And this is the value that obtains 0.24 plus minus 0.06, 0.05, which is in good agreement with Planck constraints in the last Planck data release. But for this cosmology, Planck is extremely efficient in constraining only one background parameter for the cosmology. And we have done this and here I'm showing the constraints for the cosmology where we have free curvature. We basically have these 2 parameters free to vary, of course, together with the mass distribution. And this is the constraints, again, for each cluster in different colors, and in gray, the combined constraints of all 5 clusters, which again, all the clusters, the degeneracy follow very well what we expect from the family Rachel degeneracy. And this is the value that obtained for the curvature. Is not super precise, but what is interesting to say is that it's very complementary to other probes. And this is what I'm showing here in the right figure. Now it's the constraints from strong lensing is the gray contours, and the green contour is the constraint from CMB only, basically Planck, the last Planck data release. And in blue is the combined constraints between strong lensing times Planck. And we and here I'm just showing the numbers, but what's important is this quantity here, is that for this cosmology, we improve the figure of merit of each single parameter by a factor of 1.2, which is okay, it's nice. And when we combine, of course, all the other probes, strong lensing, CMB times BAO times supernova, we obtain a much narrower constraint. The other cosmology may be the most interesting because it's the cosmology with varying omega matter and the equation of state for the dark energy, but fixing the curvature, because we kind of know more or less from CMB data only that our universe is very close to a flat universe. And in this cosmology, again, these are the constraints for each single cluster in different colors. And the gray region is the constraints for the combined probe. And as Eric mentioned here, we can see that this degeneracy, the intrinsic degeneracy of each single cluster changes a little bit with redshift. And it's nice to combine different clusters at different redshifts, because we can kind of get rid of this tail just by combining these different constraints. And here on the right, I'm showing again the combination with all the probes. Here again in green, the CMB constraint only. In blue, the strong lensing times CMB, and in red, all the 4 standard cosmological probes. And in this cosmology, given this, given the direction of the degeneracy of these two of the 2 probes, for example, CMB and strong lensing, we improve much more the figure of merit of the cosmological parameters. And basically, it's a factor of 2.5 for omega matter and 4 for W, just because of these orthogonal degeneracies. And finally, the full CPL parameterization, the results I'm showing here. Since we have 3 free cosmological parameters now, the contours are a little bit noisier because the combination in the 3-dimensional space demands more, basically more sampling. But these contours, they are robust and they are all converged. And basically here I'm showing for strong lensing only the 68% confidence level, and the combination with CMB. Here CMB on here I'm showing CMB times BAO, because CMB is also does not give very good constraints alone on this cosmology. So I'm showing here CMB times BAO in green, and the blue is the combined constraints. And we don't have super orthogonal degeneracies comparing strong lensing and CMB, but they do have some complementary. They are complementary somehow, and these are the factors of these are the improvements on the figure of merit that we have when combining Planck BAO and strong lensing with respect to Planck and BAO only. So it's a factor of 1.4 and 1.3 for all these parameters. And we yes, and basically this is the summary of this work. We of course, cluster strong lensing, it's a very interesting field, and it will be there for decades to go because of the very good new data that we're obtaining. But even with the current data that we have nowadays, we can kind of bring strong cluster strong lens cosmography to the same level or similar level to the other standard probes like Supernova, BAO, and they are all nicely complementary. Okay, it's a we are very sensitive to, especially to the equation of state for dark energy. And here I didn't say anything about time delays, but if we do have information of time delays, of course, in addition of the Hubble parameter, we can also add some extra constraints on the background cosmology on these parameters. And of course, the next generation of surveys is we provide a lot of very good data, and we need to understand better how to optimize the usage of this data. And yeah, I'll stop here. Thanks.
Thank you, Gabriel. Questions for Gabriel? Comments? So Gabriel, are you planning on working on many more clusters there? You have already shown us. So are there data already available for other clusters in the archive that?
Yes, I mean, there are other clusters. We choose specifically this sample of clusters because because we have the models already. We know very well them, and they are regular clusters. They have a relatively low number of free parameters to describe the mass distribution. We are also working on merging clusters. Everything is more complicated there, but the data, yeah, we do have data in other clusters, but it's a little bit more complicated because the number of parameters is around 30 or 35, even more. And this makes things a little bit more complicated. But at least here, we are just showing the proof of concept that this works on real data. And yes, we do have more clusters, but we also want to understand better what would be the best structural follow-ups, for example, to the large sample of clusters that we'll be observing with roving LSST, and what we can do with Euclid data, the photometric and the spectroscopic survey of Euclid.
Thank you. Any more questions for Gabriel? If not, thank you, Gabriel, again. We can move to Anna Sebron. Anna is gonna tell us about the strong lensing model of SDSS J1029 plus 2623 prospects for cosmography.
Yes, sorry, I just couldn't unmute myself. Okay. So hi everyone, and thank you to the organizers for giving me the opportunity to present some of my recent work. So today I will present a new strong lensing model of the galaxy cluster SDSS 1029 based on recent MUSE observations, and I will also discuss some prospects for cosmography with this particular system. Okay. So we have seen during the previous talks in this session that there is an existing tension in the measurements of the Hubble constant H0, and in particular between early and late type cosmological probes. So these results clearly emphasizes the need to explore and develop new complementary techniques. And we have also seen in previous talks in this session the potential of using time delays from multiple image lensed transient by a foreground galaxy. But on larger scales, we can also use galaxy clusters, and an example is shown in the right, where Grillo et al. In 2018 used time delays from the multiple image Supernova Refstal lensed by the Hubble frontier field galaxy cluster MAX 1149 to put constraints on the Hubble constant parameter. So in this work, we have analyzed the galaxy cluster SDSS 1029, which is located at a redshift of about 0.59, and is one of the few known cluster lenses to host multiply imaged images of a background quasar, in this case at a redshift of background redshift of 2.19. So these images, which have been labeled as A, B, and C, with images A and B having a large image separation of about 22.5 arc seconds. So regarding this quasar system here, Vollmeister et al. Carried out a 5.4 year-long optical monitoring campaign where they measured the time delays. So you can see here the light curves from the optical airband, and in blue, the light curve for image A, and in black, the combined light curve for images B and C, since at the time, these two images could not be deblended in the data. So a time delay between images A and B was measured to be of 744 plus or minus 10 days. And here we can note the very small fractional uncertainty of about 1%, which offers an excellent opportunity to use this system to constrain H0. So we have used, I will explain the data we have used. So on the one hand, we have used archival HST imaging, which is imaging from 3 different filters as listed here. And we have also obtained recent MUSE observations with a 4.4 hour exposure on target. And you can see here in green the footprint of the MUSE observations, which covers pretty well the central regions of the cluster. This has allowed us to securely identify cluster members and multiple images, as I will just show, in order to build a accurate strong lensing model. So regarding the cluster member selection, you can see here again the HST color composite image with in green the MUSE field of view. And we have selected 63 galaxies, which are identified as cluster members according to their spectroscopy. And we have also complemented our sample with photometric confirmed cluster members. So you can see here on the left the redshift distribution of the sources or objects that have been confirmed with a high quality flag on our MUSE observations, and here the redshift of the cluster. We have also used, of course, multiple images to constrain our strong lensing model. So you can see here the 3 multiple images of the quasar. But in addition to these 3 images of the quasar, we have also used additional images that were identified by Okure et al. 2013. And in total, this gives us 26 secure multiple images, which come from 7 different background sources. This gives us in total then 52 lensing constraints, which span a large redshift range between 1 and more or 5. Yes. So as Eric mentioned, we are using a parametric strong lensing modeling with the LensTool software. So how this works, just briefly, because it was very well explained before. So the total mass distribution is parameterized as the sum of different components. So in this particular case for SDSS 1029, we are using 2 large-scale dark matter halos. As you can see here, this cluster shows a strong bimodality and is probably cluster merging. We also include the cluster member galaxies, which, as shown here, they are modeled following these scaling relations, which relate the central velocity dispersion and the cut radius to their luminosity. We can also put constraints, as I will just show you later, on the slope parameter, and we can assume in the end a mass to light scaling, which follows the definition here, which is consistent with the fundamental plane relation. So all of the halos have been also modeled with the dual pseudo-isothermal elliptical mass distribution, which is defined here. So regarding these cluster members, we also used, in addition, stellar velocity dispersion measurements from the MUSE data. So spectra were extracted within 0.8 arc seconds, and then we used the PPFXF software to measure the velocity dispersion measurements of the total sample of cluster members. However, then to only keep reliable measurements, we follow the prescriptions done by Bergamini et al. 2019 and 2021. We keep only those with a high signal to noise ratio and stellar velocity dispersion larger than 80 kilometers per second. So we then can measure reliably the velocity dispersion for a subsample of 20 cluster members, as shown in this figure, which are color-coded according to their signal to noise. And you can see here their velocity dispersion versus the magnitude in the 160 band. We fitted then this relation, which is shown as the solid black curve. And we also did a second fitted without considering these points here, which represent the 4 most central galaxies, which are the BCGs, but some of them, because they are so close together, could be contaminated. Therefore, because these fitted relations were very similar, we adopted the one without the BCGs in the following lensing analysis. So from this fit, we can obtain the central velocity dispersion and the slope parameter here, which are included as priors on the lensing model. So we have carried out several strong lensing models with different parameterizations, and I will focus today on 2 of them. So both models assume 2 dark matter halos for the large scale dark matter distribution. In this first model, which will be called model 1, it also assumes an external shear component, and all galaxies are modeled within the scaling relations. In the second model, however, the 2 central or brightest galaxies are modeled outside of the scaling relations, so they are individually optimized. And we also assume a tighter prior on the central velocity dispersion of the scaling relations based on the observations that I just presented, on the measurements that I just presented, and as well as the alpha slope. So these 2 models, as you can see here, we can see the RMS is very similar. So we are able to reproduce very well in both cases the positions of the multiple images. And we can see here as well the total mass, the cumulative mass profile, and with the multiple images that we use in the strong lensing modeling indicated here. You can see also highlighted the positions of the quasar, which are among the further out positions in the cluster. So both of these models do constrain accurately the mass distribution and also are in excellent agreement between each other. Regarding or coming back to the scaling relations here, so as I just presented the measurements and the fit, and here in yellow and green, you can see the predictions based on the 2 strong lensing models I just presented, which are consistent with the data. So again, comparing these 2 models, we can see here on the left the critical curves, which are at the quasar redshift, and the predicted mass distribution on the right. So regarding the critical curves, you can see that they are more or less in agreement, but there are some differences on the side of the quasars actually, which are due to the different modeling performed that these two models perform on this galaxy, which is a foreground galaxy, but is included in the modeling since it's very close to image A of the quasar, and another galaxy here, which is actually very close to the image C of the quasar. And you can see here the differences of the two critical curves. And regarding the mass, projected mass distribution, you can see clearly the bimodality of the cluster. So if we come back to this quasar system here, you can see the HST color composite images with the two images labeled A, B, and C, and their magnitudes shown here. So from strong lensing models, we would expect images B and C to have similar magnitudes since they are very close together and very close to the critical curves, while image A is further out from the critical curves. So we would expect B and C to be similar and larger than the magnitude of image A. However, we do not observe this, as can be just clearly seen by eye, and we see that images A and B actually have a similar magnitude, while image C is fainter. So how can this be explained? We have also, as I mentioned, included this galaxy, which is very, very close to image C at about 0.4 arcseconds away, and can be shown here from the subtracted images. So we have included this galaxy in the modeling, as well as I mentioned this foreground galaxy close to image A. So I just give here on the left the images and what we observe just as a reference point. Here you can see the magnification map from model 2 and the ratio between the two models I presented. And you can see here the differences on the critical curves on the side, eastern side of the cluster, so near the quasar images. So here we have a table summarizing the estimated magnifications at the estimated or at the predicted positions of these multiple images predicted by the strong lensing models. So there are a lot of numbers. I will just briefly point you towards the important takeout messages. So we can see here, first of all, that in image C, if we include this hidden galaxy next to image C of the quasar, which is more prominent in model 2 than in model 1, it has a big impact on the flux ratio that we see. On the other hand, you can see that the errors on these images, on this image, but also on image B, are quite large, and this is due because these two images are close or very close to the tangential critical curves. For now, we do not observe images B and A to be similar. For now, we have not included these flux ratios as observables, and there is also a significant time variability of the quasar imaging, as I showed in the light curves in the first slides, which have not yet been taken into account and might have an impact on these measurements. So this is still a work in progress, and we hope to have more conclusive remarks soon. And finally, regarding, the time delays. So I remind you here from observations that or Meister et al. Estimated a measurement of 744 plus or minus 10 days. So from model 1 and model 2, here are the two estimates on the time delay, so between images A and B and C. So this time delay was not measured in the data, but was estimated to be about 2 or 3 days. So we can see that model 1 is in agreement with the observations within the error bars. And however, model 2, even though model 2 manages to also model very accurately the positions of the multiple images and the total mass, does not predict a time delay in agreement with the data. So yes, this again, as I mentioned, is still a work in progress, and we hope soon to have more answers. So as a conclusion, I would like to say that the MUSE observation will be made publicly available soon. We have 130 objects with the high quality flag that have been spectroscopically confirmed. 63 of them are cluster members, and 20 of those have been or have a measured stellar velocity dispersion reliably. So we have shown an updated strong lensing modeling with 2 different models, which both of them reproduce very well the observed images position while taking a lot of more data into account. So we reach around between 0.1 and 0.2 RMS for 26 multiple images. And regarding the perspective and the future, so time delays can be included in the modeling. And as I mentioned, this 1% error is very encouraging to use this system as a cosmological probe. And again, we can, with GLI, the GLI software, use or model the surface brightness of the host galaxy, as you saw in the images, as a long red arc. And with this new and larger amount of information, we hope to provide interesting constraints on the H0 parameter. So thank you for your attention.
Thank you, Anna. Questions for Anna? Sherry, I see your hand.
Hi, Anna. Thanks for the talk. So I'm very curious about this difference in time delay predictions from the 2 different models. Have you looked at the global mass distribution of the cluster? Is it because the 2 mass models give you different slopes in the profile, or what could cause such a big difference? I don't think that little perturber near image C is going to do this.
Yes, right. So I think both models are very similar in terms of the mass distribution. So I haven't shown it here, but I think they are very, very similar. And yes, the perturber may introduce some impact, but not like twice as seen here. So yes, this is a very open question for now. I think this also is very interesting because those 2 models predict very well the overall images positions, but yes, give very different time delays. So yes, I'm not sure I have the answer now.
Okay, thanks.
The critical curves are quite different between
Yes.
of the 2 models. Maybe if you can go back to that slide.
Yes. So I think the impact from this small perturber, but also from this foreground galaxy, which is more prominent in model 1. And also I think because of the external shear, which is included in model 1 and not in model 2, which may introduce these differences in the eastern part of the cluster. Yes.
Okay, thanks.
Thank you.
Any more questions for Anna? I don't think so. I don't see any other hands. Thank you, Anna, again.
Thank you.
So we can move to our next and final speaker of this session, David Keitel, search for lensing signatures in the gravitational wave observations from the first half of LIGO Virgo's 3rd observing run. Good, you're ready set, so please go ahead.
Okay, thank you. I'm very glad for the chance to talk in this session, and probably my topic is very different from all the things we heard before. I want to be honest at the start, we are not doing any cosmography yet, but I hope you will take away that with gravitational waves, we have a promising new probe to do this in the hopefully near future. So first, gravitational wave astronomy has become a reality over the past 5 or 6 years. We have this global gravitational wave detector network, the 2 LIGO detectors, Virgo, most recently Kagra in Japan, the smaller GEO in Germany, and in a few years also LIGO India. The number of detections of gravitational wave events is rapidly increasing. We are at over 50 published events now. And in the 2 plots on the right, you see the population of astrophysical sources that we found so far. This set of stellar remnants going from neutron stars to black holes with masses up to 100 or so solar masses, and going out to several gigaparsec, which is still comparatively low redshifts, but getting into cosmological range and further increasing as the detectors improve. Now, how do we detect those gravitational waves with gravitational lensing? As you all know, in light or electromagnetic radiation, it's an exceptionally productive tool across many domains of observational astrophysics and cosmology. But what about gravitational waves? So gravitational waves can in principle be lensed just like light. When there's a galaxy or other heavy mass between the source and us, the principle of equivalence tells us that gravitational waves themselves should also be deflected, the same as light. But the detection methods in science cases will be very different than for electromagnetic lensing, because it's very different data sets. And for example, the detectors have very bad sky resolution, but very good time resolutions. The phenomenology is in principle that gravitational waves experience lensing magnification, multiple images from strong lensing, the same sort of thing most people here look for, but also unique frequency-dependent deformation effects, which I mention again later. A few of the interesting science cases discussed in the literature that we can do once we finally detect these lensed gravitational waves. That includes tests of fundamental physics, like for example, the speed of light against the speed of gravitational waves from the same sources. Very precise localization of merging black holes, much more precise than the bad sky resolution I mentioned for unlensed gravitational wave events, which is really only enabled by the multiple image lensing. Then what most of you will be interested in, precision cosmology studies from lensing time delays in analogy to the quasar or supernova cases, and also microlens population studies, which could be of interest for cosmology, for example, when you think about primordial black holes as a population. A lot of the literature has traditionally focused on future detectors like Einstein telescope or LISA, which would be in the 2030s. And for these, we expect large and lensed event rates and really to realize this potential for precision cosmology or cosmography. But for now, I want to convince you that gravitational wave lensing is already exciting now with the current 2nd generation of ground-based detectors. So this current network that I mentioned before is rapidly increasing the sensitivity of each of the detectors from observing run to observing run, and also more detectors are getting added. And so we get more events and more sensitivity to rare effects. One of these rare predicted effects is lensing. Some of the recent forecasts in the literature, for example, this plot from et al. Has prediction that at design sensitivity, so just a year or a few from now, we will have thousands of gravitational wave detections in a single observing run. And from those, we would expect a handful of lensed events for the first time. Due to those sort of predictions, the interest in the community has grown rapidly, as you can see, for example, from the simple literature search for LIGO and lensing. And there have already been a lot of searches on the data from the first 2 observing runs, so-called O1 and O2 of the advanced detectors for lensing signatures. They found a few things that look like intriguing candidates for lensing effects, but it's fair to say that so far there's no generally recognized evidence for any of these to actually have been lensed and not just normal gravitational waves, or for example, in case of multiple image candidates, just independent events that happen to look very similar. Now, what I mostly want to talk about is the most recent paper in this area by the LIGO-Virgo collaboration about lensing effects in the latest observing run, or more precisely its first half, which brought this total of events up to 50, 39 of which concluded from that last run itself, so large improvement compared to before. We also call that the second gravitational wave transient catalog, GWTC2. And I have here's a link to the paper on arXiv. There's a data release associated with it, and a summary of the basic points in a more public-friendly fashion is also linked here. Now, what do we actually cover in that paper? We have a section on lensing statistics, estimating how often lensing of gravitational waves should happen and what we can constrain about that. Then we search for the basic effect of magnification in individual, mostly binary black hole and other merger events. Then a large part is searching in different ways for multiple images from strong lensing, which would appear as these repeated events within the detectors. And finally, the unique signatures of microlensing that produce frequency-dependent beating patterns in the signal. Now, on the statistics side, the idea is we take our basic understanding of the binary black hole source population and the lens population out in the universe, where the lens population is, of course, well constrained by electromagnetic observations already. We predict what the rate or relative rate of lensed to total detected gravitational wave events should be, and find typically about 10 to the 3 to 10 to the 4 events total have to be observed for every one lensed event. So it's a rare effect, but with increasing detection rates, it should become realistic, while for the current observing run that we analyzed here, it would have really been an extreme outlier to find something. Then, assuming there's no detection so far of the lensed events, you can turn it around and constrain the merger rate density, especially at high redshifts, because lensing gives us further reach, and compare that to the initial constraints based only on the local universe observation we had so far. And we see that lensing significantly constrains that merger rate density evolution with redshift. We also combined this with the stochastic gravitational wave background, which is a superposition of unresolved high redshift weak events, and from that get additional constraints on the lensing rate, magnification distribution, and overall merger rate density again. These results then also help us to interpret all the search results in the rest of the paper. The first real data analysis we did here was looking for magnifications effects. So the basic idea of gravitational wave data analysis for compact binary signals is that you measure the frequency evolution, and then you get the direct measurement of the luminosity distance from comparing that frequency, the overall amplitude, to the one predicted from the intrinsic parameters that you get out of the frequency evolution. So you can compare the frequency evolution and the amplitude, get that extra distance measurement, but with lensing, it maintains the frequency evolution in the standard strong lensing limit. So the sources will appear closer and more massive than they really are by having just their magnitude amplified. So under that hypothesis, you could think some of the very heavy events, surprisingly heavy events we found, could have a lensing origin. So we looked, for example, at the very heavy binary black holes, the famous 1905-21 intermediate mass black hole formation, and two others from this run, and thought if they actually come from more typical stellar mass black holes below the pair instability supernova mass gap, what lensing would be required to explain them. This would require relatively moderate magnifications and push them out, maybe out to redshifts of 1 to 2. So this could be quite feasible. On the other hand, looking at mergers where one of the objects is feasibly a neutron star, if you would then say those should come from the more low mass, more typical galactic populations, those would require very high magnifications and be even rarer. Overall, some of these are consistent with the lensing scenario, but there's no compelling evidence for it, given Occam's razor, that they're more likely to come from an actual intrinsic population that just goes further out than we've observed locally. Then we continued looking in several ways for multiple images from strong lensing. The idea here is the very same as in electromagnetic world, but how does it show up in the gravitational wave data? We would get a waveform that depends on all the usual intrinsic parameters like masses and spins, and basically just has 3 changes: an overall magnification factor, different for each image, a time delay between them, and this Morse phase that depends on the image type. The luminosity distance and coalescence time that we infer from it would then be different for each event, but the intrinsic parameters like masses and spins should be the same, with just that Morse phase dependent deformation of each waveform. What we did then to search for them is look at all the possible pairs of events within this catalog, identified the most promising ones with a very fast posterior overlap-based method, where you just look at the posterior distributions from each of the events, and then pass the most interesting ones on to a more detailed joint Bayesian parameter estimation, where you redo your parameter estimation analysis, combining the two data sets, checking for shared parameters and how well they match each other, and then do an evidence-based model comparison against the single runs, so assuming they're not lensed. The results are a lot of data, but basically the idea here is that we have a lot of them, those pairs that look very similar to each other when you just check how well do the parameters match. But if you do two corrections, you include a correction for the population priors, how the events, how the masses and so on should be distributed in parameter space, and for the selection effects of gravitational wave detectors. Then you get a correctly normalized base factor, and those are all as log base factors negative, and so there's no evidence for strongly lensed pairs in this catalog. But that only includes the events that are already part of the catalog. As another analysis, we also searched for fainter counterparts that might have not been seen individually before. The idea here is that if one image is weaker in a lensing situation, then you can look for the same parameters of known events and try to dig it out of the noise with matched filtering. We did this with two pipelines and found actually a slight observed excess of new events over what you would expect from pure noise alone by doing this set of targeted searches. You would expect about 2 of them, and we found 8. So a nice list of candidates that could then also be followed up again with a joint Bayesian parameter estimation. And again, the posteriors were not similar enough to overcome all these prior and selection effects, and these are not promising evidence for lensing, but it turned later out by different searches that several of them probably are just new unrelated astrophysical mergers from the background distribution. The final analysis in the paper is this frequency-dependent microlensing effect, which is something you don't typically see in most electromagnetic observations, where the size of the lens is comparable to the gravitational wavelengths, and then you get this effect that you have multiple images, but their time delays are much shorter than the typical time of the signal. So they superpose and create these beating patterns. We also can't distinguish the sky localization, just same as in typical microlensing. And then we get these strong microlensing patterns when the source is closer to the lens, or they depend, of course, on the impact parameter. How do we search for these? We use these modified waveforms, do Bayesian parameter estimation with that, or with the standard ones, compare again the evidences and do a model selection. Overall, again, we find no evidence for this effect from the observed set of events so far. All the base factors are very close to unity, no decision, and also the posteriors that we derive for the potential lens masses here, this is all assuming point mass lenses, would be very uninformative. This is just a short snippet. The total set was done over 36 such events. So the conclusion of this search on the current LIGO-Virgo data set is that we did these 4 sets of analysis. We looked at the statistical forecasts constraining the rate of lensing and of mergers from it. We looked for high mass events that were surprisingly high mass to many modelers and checked if they might be lensed, with the answer, yes, they might be, but there's not really any evidence for that preferred over the standard distributions. We did 3 separate searches for multiple images from strong lensing, or 3 related searches, I should say, and found no clear candidates. Again, several pair candidates could be from the same source, but the overall base factor is against it. And we also searched for these microlensing-induced frequency-dependent beating patterns and found no evidence. This is just the first LIGO-Virgo collaboration analysis on this topic of gravitational lensing, and it's included in the white papers for future LIGO-Virgo CAGRA analysis, and we hope to contribute more to this. To wrap up, just to give an outlook to the future and when hopefully we actually do contribute with detections of lensed gravitational waves. As I said, the network is increasing. You have this plot here from the plans for the observatories, where in a log plot you see just how much the sensitivities increase from run to run. Again, the predictions are that we should have a few first events within a few years with the current detectors. And then with the future detectors, Einstein Telescope, Cosmic Explorer, and LISA, these will have the truly cosmological reach, detecting almost all merging black holes in the observable universe. So they will really bring us to a regime of large event rates with lensing and allow much better constraints, both from direct detections and combining with the stochastic background. And once we start observing these, we can test fundamental physics, localize emerging black holes much more precisely, contribute to cosmography, and look at microlens populations in detail. This is just a set of references if people want to look at the slides later. And thank you, and I'd be happy to take questions.
Thank you, David. Any questions for David? Simon, please.
Yes, a very nice talk. I'd be interesting to, did you make predictions for quadruply imaged gravitational waves, as they may be less chance to be a background contamination? So how many...
Sorry, my mute button was somehow sticky. Yeah, so we didn't explicitly search for these in combined analysis because it pulls the computing cost up a lot. But we did check among these pairs if there are additional ones that look like they could be even triple or quadruple of the same ones. One thing to keep in mind is that the gravitational wave detectors don't have perfect uptime. There's always times when only one or none of them are online, so we might still be missing ones, or because the sensitivity is not the best at some times. So overall, we found from the subthreshold search at least one case where this, I don't know, can you still see this? If I go back to this slide, there's a set of repeated candidates on 2019, July 11, the same candidates that was found by targeted searches for different of the previously known candidate events. So there's several catalog events plus another new weaker event that all share similar parameters, but already the individual pairs among that set are disfavored when you look at the overall Bayesian parameter estimation results. So we didn't find any of those in effect.
Thank you.
More questions?
One question, please, Claudio. David, very interesting presentation. In fact, as if I have a good understanding, I see that the gravitational lensing is very different from electromagnetic lensing, and you mentioned the magnification and the repeating signal. But what about the bending of changing of the direction of a gravitational wave? It is so small and tiny that you cannot observe with actual observatories, or maybe it is it does not exist. I don't know.
Yeah, so that's exactly the big difference. So typical localizations of events so far have often been in the thousands of square degrees, or we are very happy when we're down to dozens of square degrees for an individual event. So we really can't see any of the actual geometry of the lensing situation between different images. And so one thing that we can do, if we can do the joint parameter estimation, assuming two events are lensed, and that gives us much better constraints already on the geometry. And then if, for example, we have a quad, it's even better. The basic idea here is that when you observe two images of the same event, for example, with half a year distance or so, then your detectors have moved around with the Earth rotating and the Earth's orbit, and it's effectively as if you get 3 detectors in addition and have much better sky localization. So that can already nail it down well enough that you could do detailed deep electromagnetic observations of that same area, or check catalogs that already exist for the same area. And if then you have the combined observation of gravitational waves and light from the same lens system, then you can really do a lot more with the very precise localization, check where in the galaxy did it come from, and also use it for cosmography. That's checked in a lot of detail in this Hanuksela et al. 2004 reference.
All right, so thanks, David. Probably we should close our session here, almost in time. Let me thank all the speakers of this parallel session. We really had very nice talks, and we have listened to very interesting results. Even more interesting are the prospects and the promises for the future. So it seems like cosmography with gravitational lensing has a bright future. Let me thank also all the participants to this session. Thank Mimosa for co-chairing this parallel session. And probably we can stop here. Have a good evening or good rest of the day, depending on where you're based, and enjoy the rest of the meeting in the next days. Thank you all.
Thank you. Bye.
Bye.
Thank you.
Thank you. Bye.